tutorial section. Yeah, so the first speaker will be Kuntai and Junchen. And I'll do a brief introduction. Kuntai or Junchen, please do a brief self-introduction before you start. And yeah, I guess we can get started.
Okay, yeah, so I was originally including a self-introduction slides, but yeah, I can introduce myself now. Yeah, so this is Kuntai, and I'm a graduated PhD from U Chicago, advised by Jun Chen, and I'm now working as a scientist in a startup. And well, like why am I here for this tutorial is because the Ion Cache project that we are working on, which is the main topic about this session, I'm the committer of that. And also, I also have like a VLM side committer status, meaning that I can also uh I can do I have the right access to the most popular open source inference engine, VLM, and my expertise is on LLM inference, particularly about KV cache related optimization. Yeah, I guess that's all for the introduction on my side.
Yeah, thanks, Kuntai, for the introduction. Can yeah, you can share your screen and start the presentation for the first section. You are muted, Kuntai.
Oh, yeah, do we need like Junchen to introduce himself first, or we can do it later?
Uh, yeah,
Up to
Junchen,
you. Why don't you get started then?
yeah.
I'll just get started. Okay, sure. Yeah, let me share my screen. Can you turn on the sharing? Thank you.
Uh, Let me check. Sorry, I just got the host permission. Let me see if I can. Uh, oh, host isn't allowing this. Let me see. Um,
You need help. If you want, I can grant co-host permissions to
oh,
Yuhen. Okay,
yeah. Okay, you
give
grant
us a moment.
the. Yeah. Okay, sure. Thank you.
Oh, you have do you have the authority to do that? You go to the list of participants, and
Okay.
you'll see a drop down in his name that allows you to make him co-host.
Oh, okay, okay. Gotcha. Let me see. Co-host. I can only select chat with him. How to select the co-host things.
Okay.
Um, and also I don't have the
Don't worry. I'm going to
permission to
reclaim the
do.
host permissions. I'm going to provide just a moment.
Okay,
Oh, I
thank you.
can start to send sharing request.
See if you have the permissions now.
I can share the screen now. Okay, let me see if I can make contact the co-host. Uh, let's see. Sorry, I still don't have the
Okay.
option. Okay. Yeah,
Yeah, I
I
think I
think
can share, but
contact.
yeah.
Now check.
Can you guys see my
Okay.
screen now? Or
Okay.
Yeah,
Now I
yeah,
can
yeah.
see. Okay. Fix it.
Thank
I'll
you.
be around. Okay.
Okay, thank you.
yeah. So I guess I'll just start. Yeah. Today I'm going to like give a brief introduction of why we are doing Ion Cache and why we are hosting this Ion Cache session in SIGCOMM'. So basically the goal will be after this talk you will learn about like why we start to build Ion Cache and why is it related to the networking community. So the topic of the talk will be Internet of LLM and Ion Cache as a socket of LLM. Yeah, so now let's start. Uh, First, I'll skip this self-introduction slides because I already did. Okay. And let's give a quick background on why we are on the like the very broad scope of what we're talking about, which is LM inference. So the background is that LM inference is already very huge industry. So, like traditionally in traditional learning models, like in traditional machine learning models, like maybe the convolutional neural network, training is the dominant thing. But for LLM, large language models, the inference is the key part. The reason is that only tens of companies are dedicated to training new LLMs, but over like millions of apps and organizations are running LLM inference. And here's a short quote from Jason Huang. The yeah, and the significant computational requirements for inference scaling now surpass the pre-training compute demands. Basically, currently the inference is already occupying more GPU hours than training, and this trend will even grow because there are so many startups are working on using LLM to empower their products. So we are envisioning that this trend, LLM inference, will only become even more larger compared to before. Okay, so let's quickly dive into the basics of LLM inference. Here is just a simple background. Basically, LLM can do two things. One is called prefill. Prefill, it will read the whole input. Like here, the input is this, like, is tomato a fruit? It will read the whole input and generate one token. In this example, is this it. And then during the decode phase, it will generate one more token based on previous, like it will basically generate one more new tokens. In this example, it will generate an is, like a new token is. And a token is basically you can think of it as a tag, a word in the natural language. And here we can see that there's a KV cache component here. And this KV cache is because we have this KV cache because we want to cache previous computation. Like here in this example, you can see that the decoding is generating one more token. We don't want to reread the input again. So in this case, we are using the KV cache as a caching component to cache the previous computation. Okay, that's all for the background. Now we can start to dive into the real topic. So currently, the LM inference is having a very significant trend that it transformed from using LLM as a single endpoint to agents of LLMs. Like for example, I'm not sure if you guys are using like latest LLM products like Cursor and yeah, and also deep research. Those kind of features are all like using LLM as an agent. So basically, the LLM can not only just read the text and generate new text, it can also operate. It can also like operate your code or operate the internet to search new information for the deep research, or maybe draw some new images, or maybe like think deeper and provide valuable insights. So these agentic usage of LLMs are emerging, and we are envisioning that ultimately it will become an internet of LLM agents. So we can imagine that maybe all over the internet, there's different LLM agents doing different tasks. Maybe some of them are like digging up the code and find valuable insights, and some of them are summarizing the existing websites and try to provide with the latest news. So basically, we're imagining that there will be an internet of agents that are that LMs are sitting all over the internet and they're communicating very frequently to propagate the new information from one to all over the world. Yeah. So basically, we're envisioning an internet of agents, and this is already start to happen, thanks to the recent development of MCP protocol. Basically, LM agents can now already communicate to all kinds of devices and all kinds of like system hardwares, as long as you are wrapping it into a MCP tool. Yeah. And the system challenge of this Internet of LLM is that the communication platform, the communication media, the majority of communication is done by text. And text, unfortunately, is a very slow media of communication for LLMs. And let me explain why. So here, let's dive into a quick example. For example, we have a coding agent and we have an internet searching agent. and maybe the developers start to find that the code has a bug, and it want the coding agent to fix them. And the coding agent analyzes and generate a new request to this internet searching agent. Maybe it's a here's a buggy part of the code and a very long code. Please help me find related Stack Overflow posts. Yeah, basically it starts to ask for help for an external agent. And this internet searching agent will reread the text. Basically, it will read the text generated by another agent. And this is basically caused by extra communication because if they're, imagine if these two agents are the same thing, are the same LLM, you don't have to reread everything. You just need to generate based on previous text. But now the LM agent needs to read the text and understand what does it mean, which is basically doing prefill, and this is the overhead. And then it will, after reading everything and understand everything, it can start generate new search keyword and search and summarize the results and return it back to the coding agent. So here we can see that because that the internet searching agent, it needs to read the text, it occupies a lot of runtime here. Yeah, because reading text is not very fast. It's at most thousands of words per second for large models. Yeah, so it's not very fast. It's still faster than human, but it's not very fast. Yeah, but and what's the like how can we address that? So basically, we found that KV caches is a more effective media of communication. Effective. We'll see what effective means real quick. So basically, in the previous example, imagine that not only do us send the text to the internet search agent, we also send the intermediate results represented by KV caches to the agent. And then in this case, the internet searching agent can read the text using KV caches as an auxiliary tool. And we already have a series of research works to show that with this KV cache, it can read the text much, much faster. And then after reading the text, it can generate keyword and search and then return to the user. And compared to like previous paradigm, the end-to-end time of this using KV cache to communicate of this communication is much faster. Yeah, it will save a lot of GPU cycles, and it will result in a shorter response to the end-to-end overall. Okay, so what do we do like in the previous slides? Let's do a quick abstraction. So at a very high level, the LLM will need to use a sys in order for LLM to communicate using KV caches, the LLM needs to expose some sort of syscall, and then it needs to connect to a socket for the KV caches. And after you put in the data to the socket, it can then start to communicate the KV cache using communication protocol to the destination large language model. Yeah, and this is the high level abstraction, and we see that
Hey,
LLM cache
Kuntai.
is sorry.
Sorry, there's a question in the chat. Are both
Oh, I'm not
models
sure.
the question is, are both models on the same GPU?
The short answer is no. Uh, so for like especially because like we are using the example of two different agents, they typically they can be the same model, of course, by using they can be same model with different prompt, but they can also be different models. Yeah. Okay. So are there any other questions from the audience? I don't see new. Okay. Oh, I see a new question. Oh, thanks for asking. Yeah, and the key to, we are already realizing this abstraction and it's already production ready. So basically, the production ready version of this like LLM plus syscall plus socket implementation. Oh, I mean, the order is wrong, but yeah. So basically, LLM engine is realized by VLLM, and the syscall is the KV cache connector API that is already being publicly used by a lot of open source softwares and a lot of proprietary softwares in the company. And then the socket will be the LM cache. And the LM cache this socket can already be is already being widely used by the following companies you can see, and we are already like it's literally acting as a real acting as a socket. Like for example, it can connect to different storage platforms and different LLMs, and it can transfer the data pretty in a networking way. Yeah, and so basically here Ion Cache we are using Ion Cache as a socket for LLM, and the reason we think that Ion Cache is related to to networking community is because we observe that networking is a real bottleneck for large language model for this like socket of LLM and for this KV cache communication. The reason is simple. So the source generation speed of KV caches is around 256 gigabits per second per node. And this is measured by the following setup, Llama 3.1 8V on 8H100, which is basically a node. But the public internet, like we're talking about internet of agents, so here we're using public internets. The public internets can at most achieve tens of gigabits per second per node. And this is already a pretty high estimation, given that most of our people, for example, me, myself, my computer does not have such a high internet bandwidth. Yeah. So basically, there's a significant difference between the generation speed of KV cache and the speed we can send the KV cache. And the internet is a real bottleneck for this communication paradigm. And we are envisioning that there will be more and more networking research. We're already doing it, but yeah, feel free to like start to explore this space and do your own networking research based on KV cache. Yeah, and as a quick summary, we like our artifact cache is a very we are positioning it as the socket for the internet of large language models. And that's all for this slides. Thank you.
Thanks, Kuntai. Any questions from the audience? Okay, if not, Junchen, you may start your presentation.
Let me so slide sharing. Okay.
Okay.
You guys can see the screen, right?
Yeah.
All right. So I'm Jing Chen. I'm a faculty member at U Chicago. Also the faculty PI of the ARM Cache Lab, which developed the ARM Cache project, open source project for KV caching. Kuntai gave a very good overview connecting this open source project with the networking research literature. There's a good analogy between what this project does and the networking socket abstraction. This presentation, short presentation. In this presentation, I would give a slightly more technical overview of the project. Still, there are a lot of technical meat to be covered in the future. I mean, the subsequent presentations by others, but this is sort of a more technical description of what this project is about. First of all, background, like Quentin said, inference is taking over the world. And I think the SIGCOMM networking community should also take note on this because in the near future, inference, LLM inference is going to be a very, very important problem. It's going to be even a much bigger problem than LLM training or deep learning training. Just think about how many deep learning training papers have been published in the past decade. Okay, there will be at least as many papers on LLM inference in the future. So networking literature, the SIGCOMM community should take note on this. Now, the problem I want to mention, sort of connect, motivate this project with, I mean, there are a lot of motivations behind this project. One of them is how to reduce the cost and delay of large language model inference. And this is the goal, the original goal of the KV caching project. Okay? Now, why using KV cache to reduce delay and cost? Now, traditionally, KV caching, as Kuntai mentioned, KV cache is just this internal state maintained by a large language model inference engine to process a single query. Okay, so it only exists in the life cycle of a single query and in a single engine's GPU memory. There's nothing to do about KV cache if the query completes. However, there are actually a lot of proposals in industry in the past year to sort of use KV cache beyond the scope of a single query or a single engine. And the goal for this proposal to keep KV cache beyond to extend the scope of KV cache beyond single query or single engine is to reduce delay and reduce cost. Okay, for example, the caching mechanism, so-called prefix caching technique, can share KV cache across queries and also share KV cache across engines if the same prompt has been used by different queries. CPU offloading is another technique when GPU doesn't have enough memory to hold the KV cache. You want to temporarily move the KV cache into CPU memory, and that's another way to improve throughput. PD disaggregation, if you know the literature of large language model inference, prefill decode disaggregation, also called PD disaggregation, is very, very popular in industry these days. The core of that is to transfer KV cache across inference engines. Okay, so given all these optimizations and all these proposals in the industry, there is a need to treat KV cache as sort of a persistent state, okay, to be shared, to be stored, to be transferred across engines. And that state is what interests networking people, okay? Because what's missing in the literature is an efficient KV caching layer, and that layer is a distributed layer. It's a distributed communication layer, okay? It should enable GPU to GPU transfer. It should enable GPU to CPU offloading, and also CPU to CPU KV cache transfer, and of course, the offloading of KV cache from CPU memory all the way down to secondary storage systems. Okay, and these problems are should be no surprise to the networking people why this is a SIGCOMM problem. Okay, and in fact, this open source project we will be using as a running example for this tutorial is the first open source and still the most efficient KV caching layer solution called ARM Cache. ARM Cache was originally designed as a research project with three goals in mind. First, it should provide a highly optimized implementation for all the KV caching semantics I just mentioned, GPU to GPU, GPU to CPU, CPU to CPU, and CPU to storage, all these communication semantics. And second, KV caching doesn't exist in vacuum. It should work with the state-of-art serving engines, such as VRM or SGLang. However, these serving engines and these inference engines all evolve very rapidly because, for example, over the last few years, in the last few months, on average, I think there's some work done that shows there are about 5 to 10 open source models released every week. So these serving engines changes a lot every week. And the ARM Cache project or any KV caching layer solution, they should co-evolve with these inference engines, and so it's very nice property to be able to co-evolve with them. But that co-evolving must be done by design, and so how do we do that? I will explain that in a second. And finally, KV caching layer, just like any other layers, they should be evocable. It should be called, operators or users should be able to call functions of this KV caching layer by themselves. So they're not supposed to be just a fully transparent thing behind inference engines. It should be also be interactive. Okay, operators should be able to call them to be able to access the KV cache in the system, to be able to check, to move, to delete KV caching. So just think about any traditional networking library, right? So all these semantics should also be there in place for KV caching mechanism, for KV cache management. Now, so that's the original design goals, and also over the years, we have from our research group, we have a bunch of research papers built on this library. I won't go into details. You can check out these papers. But over time, it evolved outside, beyond just the scope of a research project. Now it also have a lot of enterprise usage. I just briefly mentioned, Quentin also briefly mentioned some of the open source project, open source community projects and also commercial users. These are early adopters of the technique. And also right now, ARM Cache is also the sort of the default KV caching solution for a bunch of open source projects like VRM Production Stack, the Red Hat ARMD project, Kserve project, and also the NVIDIA Dynamo project. So it's being a long journey. What is the technical meat behind it? Like I said, the first goal of this project is to have a highly optimized performance for KV caching. So what did we do? First, it has a lot of optimization, low-level optimization to overlap the computation, the ARM inference computation with loading time of KV cache. So this is very important because KV cache loading time from CPU memory or even from secondary storage system, these things can be much slower than the cycles of GPUs. So to hide the delay of KV caching IOs, we need to overlap the loading with computation. For example, the overlap loading with the computation of the same query, or overlap loading with computation of other queries. And that gives a lot of performance gain. The other thing is batching. One thing that has the people will mention that in later slides, probably this is still high level. One thing is VRM or SGLang, those serving engines all have the abstract of KV cache pages, essentially the segment of KV cache in GPU memory. But that segment size is too small for I/O in slower devices like CPU memory or secondary storage or networking I/O. So some batching is needed so that the basic data unit will be large enough to exploit the bandwidth of CPU memory and network I/O. Finally, we also need to minimize data copy because if you have a distributed system with a hierarchy of storage devices, keeping minimum copies of the same data is important, and that's also what we have been optimizing. So besides highly optimized performance, there's also the need to co-evolve this highly optimized KV caching layer with inference engine. Here's an example how we co-evolve with the VRM project. Basically, we take a modular approach. We define a KV connector abstract, a abstraction in the VRM project, so that as long as that connector is supported in the VRM project with all these APIs I listed here. I won't go into detail, but as long as these APIs are supported, we can essentially decouple the evolution of KV caching layer, which is ARM cache, from the evolution of the serving engine, which in this case is VRM. So basically, anytime VRM changes, as long as it doesn't change the implement, it still supports all these semantics, all these APIs, and ARM cache project will be able to be integrated with VRM, the latest version of VRM, very easily. Finally, I want to briefly mention that the ARM cache project is not just a transparent library behind the serving engine. It also supports these APIs for operators. For example, you can easily call a HTTP interface to look up whether a KV cache for a given prompt is in the system or not. You can also clear the KV cache, all the KV caches in the system. You can persist a KV cache using the ping API, and all these. I won't go into detail, but basically these are very handy tools for operators and developers to decide, to determine and manage the KV cache within the system. Okay, now I want to end by saying ARM cache is just one example of such KV caching solution. There are other projects, maybe not as performant or not as widely adopted, but KV caching management, this layer is becoming a very interesting open source arena, and there will be more papers from this space, and I won't be surprised there will be more papers next SIGCOMM. Okay, so I will stop here and hand it back to Johan.
Okay. Yeah, thanks, Jason, for giving the great talk. Any questions from the audience? Okay, if not, let's go to the next session. So I'll be talking about, oh, so there are some questions uh, in the chat. Are you gonna upload the video? The uh yeah, so for the do you mean the videos, the recorded videos or slides? Yeah. I'm not sure if SIGCOMM uh chairs are going to upload.
Sorry to interrupt. It was not originally envisioned, but we are recording and we intend to upload it to the SIGCOMM YouTube channel. Okay? Rest
Okay.
assured.
Okay. Okay, thank you so much. Okay. So the next question on cache KV cache compress means quantization. So yeah, so there are several Junchen, do you want to answer the question?
Yeah, quantization is one of the ways to compress KV cache. In ARM cache, we support quantization, but also it also supports KV cache encoding mechanisms. By encoding, I mean beyond quantization, you translate you compress the KV cache into bit streams, not just tensor form anymore. I mean, one of the techniques for encoding is a paper from last year's SIGCOMM called CashGen. I mean, Yuhan is actually the first author of that, but that's another way to do compression. So I guess does that answer the question? We can, um, yeah, thank you.
Okay. Okay. Thanks for the questions. If there are no more questions, we can go to the next session. Okay, I'll share the screen. Okay, can you guys see the screen? Oh, okay, thank you. Yeah, so next I'll talk about some like hands-on experience of how to set up and install Ion Cache. Like in okay, so I'll get started. So there are several ways to install and use Ion Cache. Like one way is you can install Ion Cache on your local servers with pip install. And you can also install the Ion Cache code from the latest source code. And I'll also talk about two another ways to use to directly run Ion Cache. One is with a pre-built Docker image, and another one is example usage of using Kubernetes to deploy Ion Cache with VM's production stack. And there are also Junchen mentioned like there are several other open source Kubernetes framework, Kubernetes project that can use Ion Cache, but I'll just use VLM Stack as an example. Okay. So the first way that you can install Ion Cache is to just install it locally with our PI package. And to do that, first you can just install VLM, which is a prerequisite of Ion Cache like packages. And then like you can just run pip install on cache to get the necessary packages for it. And so next, like I will show a demo video to do that. And to verify that you have Allen Cache successfully installed, I'll also include an example. And so the key is like you can start a VLM server. VLM is the one of the most popular inference engine nowadays. And like you can start a VLM server and use Allen Cache at the KV cache management backend. And so first, like basically you can just run here. This is a standard way to start a VLM process to serve a Llama 3.1 AB model. And if you want to use on cache, you need to pass in an environment variable that specifies a config file for on cache. And here it's environment variable on cache config file. And another thing if you want to use on cache as a backend is you need to pass in the KB transfer config and specify on cache connector as a connector between a VLM and an on cache. And this connector is what Junchen Quinta has talked about briefly, which is the VLM can offload the KV cache to with this on cache connector. VLM can offload KV cache to lower tier storage. Yeah, and you can also configure Allen cache with this Allen cache .yaml file. And so I'll use a very simple example to illustrate. But like, so there are some, if you want to offload KV cache to CPU memory, then what you need to specify in this Allen cache .yaml file includes this chunk size, which is like the like what Junchen talked about, like the chunk we don't manage Cache doesn't manage KV caching in page granularity, but in a higher granularity for IO efficiency. And here, like we can specify the chunk size to 256, which is the default chunk size in Allen cache. And then if you want CPU memory, then you can specify local CPU, can set local CPU to true. And you can also set like a maximum of CPU memory you would like to use for on cache. So if like the KV cache you want to offload exceeds this CPU size, then it will be evicted. Okay, I saw some questions in the chat. So the first question is, how should the model be installed? By install model, do you mean like how to download the model or how to set necessary packages? Um, Okay, so let me guess. So if you want to install the packages, the necessary packages for it, okay. I mean, what if I want to use another model than Llama? How should I install? Okay, good question. So if you want to use another model, like here, for VLM, it supports any model on Hugging Face. And if you want to have another model on Hugging Face, then you can just change this Meta Llama 3.1 AB instruct to another model name that you can get on Hugging Face Hub. Does that answer your question? Okay. Uh, Thanks. The next question is, can I do on a MacBook without GPU? So, technically, yes. Like you can install it on install like VLM and run on CPU machine, but it will be pretty slow if you do it on your local MacBook. Does that answer your question? Okay, thanks. Um, okay, so let's continue. And so there are also other kind of storage devices you can use on cache to offload KV cache to. And so another example is to use a local disk as a offloading device. And here you'll also need to specify the chunk size, which is and also you can specify the local disk. And here, this is just a example that you can use like say 5 gigabytes of disk memory to offload KV cache to. Yeah, so and here I put a QR code here, like you can check, like there are different other storage devices you can use on cache to offload KV cache to outside GPU memory. And yeah, feel free to check it out if you are interested. Yeah, then I'll show this demo video that how you can install cache with just simple pip install. Okay. So here, first, you can use UV virtual environment. Here, it's just creating this virtual environment with Python 3.12. And then you can start activate this virtual environment. And then we can first install VLM. And after that, we can install Elm cache with just UV pip install Elm cache. And you can also verify if the Elm cache has been installed. So here you can see that Elm cache point 0.3.5 is successfully installed. And then let's use a simple example to start a VLAN server that serves Llama 3.1 AB instruct with the CPU offloading. Here you can see that we specify the Elm cache config file to this config that's specified in this previous slide. Okay, let's wait for VLAN server to start. Okay, so now you can see that the VLM, the model, the Llama 3.1 AB model is started to load. Okay, so the VLM server is now up. And then we can start to send a request, like on the right hand side panel, you can see that we start to send a curl request to query the Llama 3.1 AB instruct model. And after sending the first request, like you can see on the left-hand side, there are some logs from the on cache side. Like you can see that it started to store 31 out of 30 out of total 31 tokens. So this means that on cache has like the KV cache has been offloaded to CPU memory by with on cache. And then if you start if you send another request, one sec. So you can see that on cache on the left hand side, there are some logs from on cache that retrieved 31 out of 31 total tokens. So this is just a very simple example, and we will see more this kind of example in later sessions. Okay, and So this is for installing with pip install. And so the next option for you to use Ion Cache is you can install Ion Cache from its source code. So the benefit of this installing from source is that like you can access to the latest version features and improvements from Ion Cache. And if you want to do some local development on Ion Cache, then if you install from source, then you can just modify the code and see the changes immediately when you use it. And if you want to contribute back to Ion Cache project, then you need to install it from you need to clone the repo and then install from source. Okay. So to do that, you can first do git clone the Ion Cache project, and then you just go into the Ion Cache directory, and then install VLM as a prerequisite, and then install pip just do pip install -e dot no build isolation. So this is another way to do that. And similarly, let's take a look at a demo video. And similarly, you can just create a virtual environment with UV. And after you activate the UV environment, then you just do git clone to clone the latest repo. And then we go into Ion Cache directory and do pip install VLM. And after that, we do pip install -e dot to install Ion Cache from source. And for this, you may need to wait for a longer time than just simple pip install Ion Cache. Okay, let's skip this part. And similarly, after you have installed Ion Cache, then you can start a VLN server with a similar command as we have done before. And similarly, after the VLN server is up, we can submit a curl request to query the Llama model. Okay, so that's a second way to install Ion Cache. Any questions so far? Okay, if not, let's go to the next one. So the previous, okay, there's a question. Can it be used with Olama? So we currently don't have integration with Olama, but we have integrated with SGLang and BLM, these two inference engines. Okay, thanks for the question. Okay, so the previous two ways to install Ion caches, you still need to like install the packages by yourself. Alternatively, if instead of installing it locally, you can just run Ion cache with our pre-built Docker image. And so we have this Docker image called like under Docker Hub account Ion cache. And the Docker image name is VLM-OpenAI. And so they are like you can choose to use either the latest tag, which has a stable release version Ion cache, and or you can also use the latest nightly, which contains latest changes in the Ion cache source code. And to run that, you basically can use this command to do Docker run. And you need to specify NVIDIA runtime and use GPUs. You can also set all if you want to use all the GPUs on your server, or set to a specific number of GPUs you want to use. And then like instead like a easy way to pass in the Elm cache config is to just pass in the Elm cache config through the environment variables when you start the Docker image. Previously previously you have this like chunk size, local CPU, and max local CPU size. And if you want to use that with like pass it in with environment variables, you can do on cache chunk size set like through in this way uh, to specify the environment variables. And then like you may also need to specify the network as host if you want to export the port for like if you want to like so that like you can submit a curl request to the VLAN server outside the Docker container. And then you can use the on cache latest nightly or latest tag to start this to serve this Llama 3.1ab model. And similarly, you also need to specify the KV transfer config. Yeah. So let's take a look at this simple demo video to see how to run it with Docker. Okay, so here on the left-hand side, I type this command into the terminal. And let's wait for VLM to start. Okay. So now you can see that the VLN server has started with cache enabled. And then on the local server side, then you can submit a curl request to query on VLN server. And you can also see the logs that on cache is storing KV cache for 31 tokens. Yeah. So there's a question in the chat. Is there a separate compatibility table between the VLN version and the Ion cache version? Good question. So we currently don't have this table. But like we could include this table in our documentation later. Yeah, this is a good suggestion. Thanks. Yeah, thanks for the question and suggestion. Okay, so this is for running Elm cache with Docker image. And the last one is to that you can run Elm cache, can use Elm cache with Kubernetes. So I'll use this VLM production stack as an example to show how to use it. So just a very quick introduction of VLM production stack. So it's a Kubernetes native deployment that's powered by Elon Cache as a KV cache management backend. So basically, once a user submit a request to VLM Present Stack, then the request is first goes to the router, and then the VLM Present Stack's router will send requests to different VLM engines. And we have the Elon Cache backend that enables the sharing of KV cache across different engines. And of course, you can also, for each VLN engine, you can offload KV cache to its local CPU memory. Okay. And so another, oh, yeah, sorry. Thanks for sending the compatibility table. Yeah. Okay. So the Okay, so if you want to use Visual Implementation Stack, then here is a very simple Kubernetes configuration you need to specify for Presence Stack. And here we are using, for Presence Stack, we are using Helm chart template, and users can just write this very simple configuration YAML file. And so the key in this configuration YAML file is the repository, the Docker repository for the VLN engines. You need to use Elon Cache Docker image to use Elon Cache features. And another important thing you want to do if you want to use Elon Cache is you need to specify this Elon Cache config, and you can set it to true, the enable field to true, and specify the CPU offloading buffer size, which is basically the max local CPU size in the config file that we have talked about before. And here I'll show a very simple demo video to show how can work with how can start on Cache with VLM Present Stack. And before that, there's a question: do you have any benchmark that demo to compare VLM and Elon Cache plus VLM? I would like to know how long the input tokens that makes uh, Elon Cache and VLM significantly better than VLM only? Uh, Good question. So we do have several benchmarking blogs, and we are going to have a technical report for Elon Cache soon. Let me show it after this talk. I'll send it in the chat. Okay. Another question is, does Elon Cache help more with multi-model setup as well as then single model setup? So by multi-model setup, then um so uh I think in both like multi-model setup and single model setup, cache can similarly helps. However, like if you want to have more optimization, such as we are going to have a feature from cross-model KV cache sharing in Elon Cache. In that case, like that feature, that cross-model KV cache sharing may have more uh, speed up. Actually, sorry, let me take it back. So I would say like in both multi-model setup and single model setup, Elon Cache can similarly bring a lot of benefit. Or are you thinking of more specific scenarios in multi-model setup? Okay, thank you. Okay, so let's take a look at the demo video for production stack. So here we have this production stack repo cloned in the server, and we enable on cache with this on cache config, and then we do helm install. Here we use VLM as a release name, and we install Helm and specify this config file as the the YAML file to install the Helm deployment. And after this installation, you can use cool control get pods to to monitor if the pods within cache has been successfully started. And you can also do cool control logs dash f to see to monitor the status of the VLN server. And here, as you can see, if you do cool control logs dash f, then you can see that the VLM server is starting, and on cache is also successfully enabled and it's starting. And in the meantime, we can start to do port forward. So if you do this command, cool control port forward, then then you can submit any request from outside the Kubernetes pods to the VLN present stack router. And then on the left-hand side, it's starting the production stack deployment. Okay, let's wait for the VLM deployment to start. Okay, now as you can see, the VLM server has successfully started, and if you query, then the production stack will send health to the VLM pod, and then it also successfully returns 200. And then we can start querying the Llama 3.1 AB model by sending the request to port 30081. And on the left-hand side, you can see that um, the the request has been successfully received, and the Elm cache has stored KV cache for this 8 tokens inside CPU memory. Yeah, so these are several ways to install and run Elm cache. And here I'm listing several resources and support you can get if you find any issues running and installing Elm cache. Here are the docs page for Elm cache and the GitHub repo. And if you want to get support from our team, you can join our Slack channel for discussions and help. And you can also submit issues or PRs if you find find any issues, any problems when you install Ion Cache. And also, if you want, you can follow our Twitter for updates. And you can scan the QR code here to join our Slack community. Yeah. Okay. Thanks, everyone, for listening. Any more questions, comments for us? Slack link is no longer active. Let me check the do you mean the QR code? Okay, let me check. Mm. Okay, let me send I'll send a link to the latest slide. Okay, yeah, thanks, Kobe. Yeah, I can click on the link to join our Slack channel uh as specified in the chat. Thanks. Okay. I will also send Kobe, can you find several benchmarking blogs that we have published before? Uh like there is a question before.
Oh, okay. Let me try it.
Okay, thanks. If there are no more questions, we can have several minutes break and before the next session. uh, that kind of a separate loading and management of KV cache in GPU inside VLM. So I would say it's a separate module instead of building upon it. But like it definitely has interaction between the uh, on cache loading and VLM. Yeah. Another question is there a dedicated performance analysis table or benchmark report for CPU, Redis, and Mooncake? We currently don't have a published benchmarking report for now, if I remember correctly. And but we will soon have a technical report which has this benchmark number, and we will do a we will have the technical report on archive soon. Yeah. Thanks for the questions. Okay. So I think we can get started for the next session. Uh, so the next speaker is Huaizhen. And Huaizhen, let me do a brief introduction for Huaizhen. Huaizhen is a research scientist at Biden's United States. He received his PhD from Nanyang Technology University, Singapore. His research focuses on ML system and large language model infrastructure. He has published more than 20 papers in top conferences such as New Europe's AAAI and ACMM. And he serves as a reviewer for ICLR, New Europe's ICML, and other leading venues. His open source MLSys projects on GitHub has accumulated more than 7,000 stars, widely adopted by the community. Okay, Huaizhen, you can start sharing. Let me make you the co-host and so that you can share screen and co-host.
Okay, thank you.
Okay, can
Actually,
you?
as the introduction, yeah, it's 2 a.m. for me. I just feel my brain is dead. Yeah, so if I say something wrong, yeah, please forgive me. Yeah, I will give very short and very short talk.
Thanks, Huijun.
Yeah, today we are going to talk about the how to build a deep research agent with open source tools. Actually, this is the joint work from the LM Cache open source community, including me, Yuhan, and Yihua. Yeah, and yes, here is the outline, and we will first talk about the background and challenges, and then discuss the opportunities and from the open source community. Then we will discuss how to build your own deep research agent. And then I will give a short demo and show the future directions. Yeah, basically this is outline. If you have any questions, feel free to ask. The background and challenges, as I'm not sure how many of you are using deep research. To be honest, I use deep research, from ChatGPT and Gemini almost every day. Yeah, and every time I have some questions, I will first through these questions to ChatGPT or Gemini, and then turn on this deep research functionality, and then let deep research to draft a report for me and guide me on this topic. Yeah, this is a very very popular feature from this LM from this LM products, but it is very very expensive, and also you can only use maybe 30 times per day or per week. I don't recall. Yeah, but almost I use this feature every day, and so given that it is super popular, super useful, but very expensive, so I wonder if we can build our own deep research, and use some open source tools, use some open source LLMs, so we can save the cost, but and also enjoy the limited deep research features every day. Yeah, so basically this is the motivation. So I did a little bit, I did some surveys, and I found, we can use LangGraph, we can use Tavily, we can use VRM and LCache to build this deep research engine agent. Yeah, basically this is the framework of this deep research agent. First, users can input their questions to the agent, and agent then decouple this question into several small questions and small queries, and then use some web search tools to search results, and then we will have a reflection agent. This reflection agent will will think, if we need to add more research results, if so, and we will run these web search tools again and to get more results from the internet. Yeah, so this is what this reflection agent does. And after several rounds search, and if the reflection agent feels okay, the context is sufficient, and then it will send all of these contexts to the answer generation agent, and to summarize the final report as the answer. Yeah, basically, this is a very simple framework, simple workflow, and we use LangGraph to build the LangGraph to build the agents, and we use Tavily to do the web search, and we use VRM and LM as the serving engine, and we use Q13 as our LM, as our backend. And actually, after I have this design, I feel, if I running all of this VRM and RM cache and Q13 is very complicated. So I asked for the Yuhan and Yihua's help. So if we can, how can we for example, quickly launch ARM with just one click. So they provide me this ARM Ignite service, and this is a holistic and one-stop solution. The ARM Ignite includes ARM cache and VRM and also production stack. With just one click, we can launch all of these services within several minutes. So I try to use this service and to launch this Q13 model, and and without any issues, we start this service. And also, as you can see here, we also have a longsmith background, which means every time you input a query, you can see the whole workflow. You can break down the whole workflow and see each steps output very clearly. And this is the front end of this demo. And for example, we can ask what is the SIGCOMM, and send this query to our own deep research agent. Within several minutes, and we can get a very simple report from our own deep research agent. Yeah. So as you can see here, and after the first round reflection, and the agent thinks the context is not sufficient, so it starts the second round search. So you may ask why, so its agent still thinks this is insufficient, but still output the final answer because we set the maximum retry number is two, to save time. So it will only try two rounds of web search and then give you a very simple report. Yeah, basically that's your own deep research, built by open source tools, including LangGraph, Tably, VRM, and the LLM cache. Yeah. And that's it. I think, this is a very simple demonstration of how to use open source tools to build your own agents. And our future directions may include, for example, contribute back to LangGraph, VRM, and our cache communities. And also, we are doing some optimizations on this agent to see if we can further save users token consumption, and to share more practice with all of you. And the last is we are trying to build a more comprehensive open source infrastructure, not research infrastructure, open source agent infrastructure to support it. Anyone can build their own agent, within several minutes. Yeah, basically that's our today's presentation of how to build your own deep research agent with open source tools. Yeah, that's all. Thank you.
Thanks, Huaijun, for giving a great demo.
Any questions? Yeah, open to any questions.
Is the
Yeah,
demo
yeah, yeah. We will
code
release
open?
the demo code, yeah, tomorrow. Yeah. 朱琪, you are here. Yeah. Interesting. 朱琪, are you in SIGCOMM now? Hello, hello.
Yes, yeah.
You are
I'm
in SIGCOMM.
I'm Coimbra. Yeah.
Oh, I see. Juchi has a very amazing publishment, a paper in this year's SIGCOMM. Please go to his presentation.
Nice. Okay. Any other questions? Things you
Yeah,
want to share?
yeah. We will release this code tomorrow, and if you have any questions, you can, raise an issue in that repo. No problem. Yeah.
Yeah. Okay, if there are no more questions, so the next session, uh, we have a 30 minutes morning coffee break. And so the next session will continue at 11 a.m. Least like Portugal time. So about we have about 15 minutes break. So yeah, feel free to come back after 15 minutes. And our next session will also be talking about building agent application with Xeon Cache, and it will be presented by Chen Wang from IBM. Yeah. Okay. See you all later in 15 minutes. Thank you.
See you all in 30 minutes.
Uh, sorry.
No, I was just replying to you. No problem. I will say see you all in
Okay.
30 minutes.
Yeah. Thank you. Okay, welcome back, everyone. Let's continue the tutorial session. And our next speaker is Chen Wang. And I will do a brief introduction of Chen Wang. And yeah, Chen, you can take over later. Okay, so Chen Wang is a senior research scientist at IBM Watson Research Center. Her research interests lies in Kubernetes container cloud resource management, native AI platforms, Gen AI inference fine-tuning system, and applying AI and ML in cloud management. She is an open source advocate, a Kubernetes contributor, and open source summit speaker, and a KubeCon speaker and reviewer. She has authored work cited over 900 times with an Edge index of 15 and has received multiple prestigious honors at IBM Research, including the Outstanding Technical Achievement Award and Outstanding Innovation Achievement Award. She was also recognized as one of the IBM's youngest master inventors with over 45 filed patents. She obtained a master and a PhD degree in the electrical and computer engineering from Carnegie Mellon University. Okay, Chen, you can start your presentation.
Thank you, Yuhan, for the introduction. So, can everyone see my screen?
Yeah.
Okay, so today really early morning session for for people in the US. And yeah, this is really I've been working in IBM research. My main the research topic recently is on inference platform. So that's why I got very interested in cache. And I also, in my free time, developed a RAG and agent system just for fun. So that's why I kind of developed some agent and tried cache. And I want to show some demo here to give you a hands-on experience. Hopefully, I can share the code with all of you after the session as well. So let's start. So as the background, let's first introduce like Gen AI agent and dynamic reasoning. So these agents are large language model based frameworks that enable multi-step reasoning, adaptive kind of adaptive decision making, and interaction with the external world like function calls and tools, right? So this is very different, fundamentally different from conventional large language model inference, which simply just map a single input to a single output in the one forward pathway. So dynamic reasoning is an iterative process through which agents operate, continuously cycling between like internal reasoning logic and external actions. So this powerful approach is a form of like test time scaling, meaning it's a method that improves performance by adding more and more computation during inference. And then those computations actually do not change the model parameters, so they don't need fine-tuning, but they just try the inference more and more time with proper prompt, and then they kind of like enhance their reasoning capability. And one way to enhance the reasoning capability, it also introduced significant computational cost and also hard challenge at the system and infrastructure level. So the shift from static query to dynamic reasoning really create kind of like four major system bottlenecks that we must address. So firstly, the agent process is really a sequential dependency bottleneck. So an agent's workflow really requires like a tight sequential dependencies between its reasoning, which is the inference and its action, right? So for example, when the LM determines what tool to call and the tool's observation becomes the input for the next inference, so you are pending. So you are actually, the next call is strongly dependent, temporally dependent on this call. So the serial process cannot be easily parallelized, and it create fundamental like sequential bottleneck in the agent's end-to-end latency, right? We can't reduce it because it's a sequential steps. Second, the workflow actually leads to GPU underutilization because it interleaves the GPU-intensive inference with CPU-bounded tool calling or IO-bounded tool calling. So during the tool execution phase, the GPU often remains idling, waiting for the tool's response. So there is a analysis from this paper. I'm going to cover most of its results. The paper actually shows that the GPU can remain idle for as much as like 50%, over 50% of the total execution time. And this is a huge waste of really scarce resources we have today, which is GPU. So third, we face a very variable latency distribution for those agent response time. So unlike traditional or conventional inference, which we kind of have the predicted typical latency according to the input and output tokens and the model size, right? Agents actually exhibit very variable multi-step execution times. So the number of reasoning steps, tool calls, all vary widely based on the task. So it results in a very heavy tail latency distribution. And the small number of complex queries can take a disproportionately long time to complete. So you will also see it in one of our demo, in one of our agents. So a particular 2 or 3 steps takes much longer to finish. And then, so finally, the iterative nature of the sequential nature of the agent workflow actually causes increasing memory usage. So as an agent process, it appends its past large language model output and 2 responses to the next inference input in each step. And this accumulation of history tokens leads to rapidly growing input size and very large KV cache footprint. So it puts a significant pressure on GPU memory. So the conclusion is, how can we improve the compute efficiency of those dynamic reasoning agents? Now becomes the critical question. So to understand those challenges, we need to look closely the agent's core workflow. So as you can see on this slide, an agent process is not a single linear operation again. At least 2 phases, iterative workflow that alternates between inference calls and which is the reasoning phase, and the tool use or external interaction, right? This creates sequential bottleneck, dependency bottleneck. And then, so specifically, like, according to the paper's analysis, this latency breakdown shows that the inference time account for 70% of the total latency, while the tool calling at least makes up around 30. And then this multi-step workflow also results in a very high number of iterations. And with tool calling, with complex workflow, they are showing, and actually it can make 9.2 times more cost than conventional single pass inference. So for some agents that use tree search strategies, this can escalate to dozens of calls of a single user query. So about the resource underutilization, and then the agent workflows can alternate between GPU-bound inference request and CPU or IO-bound tool callings. So GPU often remain idling during the tool calling phase, and then the data shows that the GPU can remain idle for as much as more than 50%. So back to the basics, we want to review what is the KV cache a little bit because we need to estimate like how much KV cache we can reuse in a dynamic reasoning agent, right? So as you can see from those animations, right, the KV cache is specific type of memory that stores previously computed K and V tensors from the transformer attention layer. And why it is important for inference? Its main purpose is actually to reduce redundant computation. So think of it as the model's short-term memory. So by reusing already computed attention states, especially for the shared prefix from the input, the model can generate response much faster, so it doesn't need to recompute it. And large language model inference happens in two phases, as we all know, like prefill and decode. And then we have prefill phase where the model says all the initial context you provided all at once, and then the phase can be so for example the whole question or the whole paper PDF, so the phase can be optimized with something called like prefix caching. And then next, more important for our discussion is a decoding phase. This is where the model generates new tokens, new words, and then this phase is really memory bound. It can take up a significant part of GPU execution time. However, it's memory bound, so it takes a lot of memory and your compute is underutilized. So when the model generates a new token, it needs to consider all the previous tokens and all the pre-filling tokens. So at least all your pre-filling tokens needs to keep in the memory. So this way you also have fewer space to batch more requests from others, right? And that's the core reason why it leads to underutilization. So then we connect back to the agent, the dynamic reasoning agent application we want to develop, right? The agentic AI system often involve very, very long conversation, very complex reasoning chains, and then all the previous information are appended to the next round of reasoning. So imagine AI agent is helping you to solve a multi-step task, and the conversation actually goes on with some background material like a document and go dozens of turns. And then the context window grows significantly. Therefore, the KV cache expands a lot. And then memory becomes the critical bottleneck to scale such agentic applications. Your GPU is underutilized and everything is slow. So first of all, compute efficiency, you can do prefix caching. So instead of recomputing, you can kind of like keep all those KV cache in GPU memory, and then reduce the prefill latency by around like 60%. However, if you have a lot of long decoding sequences, and then you still need to keep all of those in GPU memory for a long time. So during that period, your GPU is underutilized. And second, we want to address the memory challenge. We can implement the KV cache sharing, right? And this would be incredibly effective, reducing memory requirements up to like 60 to 70%. So while the ever-growing KV cache in agentic workload, presents a significant memory and compute challenge. And techniques like prefix caching and KV cache sharing can turn this problem into reuse opportunity, dramatically improve both the latency and memory efficiency. However, we have some problem. We have memory bandwidth bottleneck, right? Okay, so again, this chart is really showing like if you have limited amount of memory for limited KV cache capacity, and then your KV cache capacity will significant impact your AI agent throughput, right? And the number is not even from AI agent, it's just from the one pass query. And then you can still see that if you increase the memory for KV cache, you get much larger throughput. Okay, that's precisely the problem that Cache project is solving. So Cache is designed to provide a system for fast dynamic loading and offloading of the KV cache. It can give you the best of both worlds, the performance of a large cache without the constraint of limited GPU memory. So it aims to optimize for time to reduce TTFT, which is time to first token, and to dramatically increase your throughput and GPU utilization. And so how does Cache achieve this? I'm sure through today's tutorial you learn a lot of it, but just going through two key technology, right? The first one is high performance CPU KV cache offloading. And they really achieve that by cache gen because they do very effective compression, and then they can improve the transfer of KV cache very fast. So they overcome the limited bandwidth between GPU memory to CPU memory or even to a disk. And then, of course, they also support disaggregated preview using the NICO, right? And then they also enable the peer-to-peer KV cache sharing across instances. But eventually, what makes it very, very useful for agentic applications is assuming you have right now unlimited pool of memory for KV cache, and they have a very efficient way to to manage the offloading of KV cache. So from the real measurement, by combining cache with VM, developers can see 3 to 10 times faster response cycles. And so because the response time is shorter, and then your overall utilization is higher. So to easily use cache, the team from Chicago also built the production stack. It is a reference implementation that takes all the complexity of integrating with VLM, deploying VLM, routing models, taking all of those complexity out. So you can do the one-click deployment with all the necessary components you need together with cache. So of course, production stack, the unique part of production stack is that it's the native integration with LM cache, and then it enables KV cache offloading. And we will see how those agents can be integrated with deployment with cache using production stack. And you don't really need to worry about the operational complexity because they provide either Helm chart all the controllers for you to do one-click deployment, and their controller will handle the availability of your router and your VM runtime servers. So next, let's dive into some practical part. So we actually developed several agents, but I am here due to the time limit, show two demos of two agents. The first one is, you may all be interested about it, is a paper review agent. So we want to demonstrate that so to help us to solve the problem, time-consuming and tedious process of reviewing paper, and so we want something to automate this process, and we actually develop it using long graph. So the paper is the input, and then through a series of automated sequential analysis steps, it will generate a comprehensive and insightful review. And then this means instead of spending hours of reading it, you can get a brief idea from AI what the paper is about, and if there's some apparent flaw about the paper. And so we actually integrate this paper review agent with deployment of VLM without Mcache and with production stack that is integrated with Mcache. And we see how Mcache can significantly improve the this agent application in terms of response time. And this agent is actually an ideal test case for Mcache because firstly, there is a shared large document context, which is the paper, right? And second, it actually uses iterative refinement because it's building up the reviews. It needs to understand different different important aspects of the review and merge them together. So it's an iterative process to go through the large context of PDF. And then it involves long document processing, so it will make the context window prefilling very long. So in terms of implementation, it's we will open source it later, and it's implemented in LangGraph, and then to load the PDF using PyPDF loader. And for other details, you can check the code. And let me see if I can just quickly fast forward the video. Okay. So you want to go to this Mcache repository, and then we will open source this Mcache agentic repo. And then it works with both production stack and Mcache endpoint. And it's developed in using like LangGraph, right? LangChain libraries and LangGraph. And the UI is using Gradle. So it really have a dual agent comparison. So it compares two same agents connecting to different backend endpoint. And then you can actually try it locally using Docker, or you deploy to on Kubernetes, and it's even provide a hand chart for you to quickly deploy it on Kubernetes. So here we will try the simplest one, which is just use kube control apply to create a YAML. So those are the 10 steps of iterative process of paper to come up with the review. So the left side, we will configure it as VLM, and you can also configure it with other endpoint like OpenAI, Cloudy as you want. And so I already tested all of those models, but it doesn't mean it's limited. So as long as you have the same endpoint, you should be able to try different models. So let me speed it up a little bit. So first we want to configure the config, and then you probably want to change your OpenAI API if you want to use the OpenAI model. And then the easiest way is to pull the latest image from the Cache Docker Hub. And you can configure the volume mount to keep your logs locally on your node. So let's go ahead and create the Kubernetes deployment as I was testing it because I already created, so I don't really need to do that again. And then, so the easiest way to see this UI is if you are on the remote server, you want to do the kube control port forward to your local host. So I was having some issues with port forwarding. Okay. Actually, you can see those. You can also open a window to look at the logs of those. And then, so this is the UI. And the left part, we configure the VLM endpoint. The right part, we configure the VLM with cache. You want to put your API key here. We actually put a very long PhD dissertation and trying to stream the logs to the UI to see how long it takes for each steps of the workflow. And then you can see cache finish first, and then total time is 10. And this one VLM actually takes 28 seconds to finish, so almost 3 times. And those the below are two generative review in Markdown format. So this is one. Let's go back to the presentation. You're welcome to try it after the session. Let's skip this. Okay, so another agent I'm presenting is based on the framework called Diffie. Diffie is really the no-code agent building tool. So you can build anything, even without one line of code. You just drag the modules, and it's pretty easy to use because you can easily deploy it using Helm chart on Kubernetes. You can even start it using Docker on your local laptop, and then it configured. So it's really production ready framework because it even configured all the Redis, the event hub, like a login credentials database, so it will start everything for you. And it supports multi-user access. And then, so users, so here we actually drag the module to have a research paper chatbot. So if you really want to dive into the research paper, you can first use the research paper review agent to have a brief idea and then ask a question about this particular paper until you understand all the details. And so let's just go ahead to see how we can quickly start Diffie. Let me share this. Okay, I'm going to speed up a little bit. So again, this is the same repo. We only keep the tutorial and the Diffie configuration DSL file called VLM versus Mcache YAML. And so here you will have the Diffie paper chat. Again, it's also under cache. And then you go clone this one from Longinus. You can clone the Diffie repo, and then you just need to change the environment variable to configure your own token and initial password. Here we configure it as cache. And you actually need this password to register your own account in this platform. Because this is not the first time I started, but all you need to do is to clone that repo cd into Docker, do Docker compose up, and you will get this studio. And I already registered it. The first time you register, you may need that initial password. And all you need to do is to configure those blocks. So here, what we configure is to take a PDF connecting to two backend. One is VLM with the one model, 30B. The other is the so here you can change the credentials, configure API key endpoint, even the context window. And again, you can use another model, for example, OpenAI API compatible provider. So you can install a lot of those model providers manually by going to your account setting, model provider, right? And then here, both of the backend, we set it up with the Q13 30B model. And the output is really, we output the text and we also output the decoding tokens plus the time. So here, when we do publish, and we will have like ChatGPT-like window, and then you can now get some prompt. So I have some example prompt here in the GitHub repo as well. Let's just summarize the contribution in one sentence. So this is a really long input. So you can tell, like here, Cache is responding in 1.5 seconds, and VLM is responding from 3.67 seconds. And this is a PhD thesis with 2.57 megabytes of the size. So later, I'm just alternating a lot of different PDFs and then switch between and to see the consistency of those latencies. Okay, so I think I'm almost running out of time, and I'm just going to wrap up. Okay, so those are the latency comparisons of those two demos, and then we will keep open sourcing more and more agents similarly. And then you can also check, like during high concurrency, what would be the throughput, overall throughput, memory usage or utilization you improve, right? And so again, the project we have been using to develop those include like Mcache, production stack, and you can check the documentation how to install those. I'm sure Yuhan also gave you some tutorial early in the morning. And then for this tutorial video and demos and code, we will also open source those. So that's it. Yuhan, back to you.
Hey, thanks so much, Chen, for giving the great talk. Thank you.
Okay.
Yeah. Any questions from the audience? Hey, if there are no more questions, let's go to the next speaker, Zhuohan Gu. And I'll do a brief introduction of Zhuohan. So, Zhuohan is a PhD student at a first-year PhD student at MIT CS department. His research interests lie broadly in computer systems and machine learning, with a recent focus on machine learning and LLM inference and AI infrastructure. He works on high-performance KV cache management in LLM serving, including KV cache compression, PD disaggregation, and KV blending and editing. Johan is also a community builder for two open source projects, LLM Cache and VLM Production Stack, as a member of the LLM Cache Lab. He graduated from University of Chicago in 2025 with a bachelor degree in mathematics and computer science. Okay, Johan, you can start sharing your screen and start the talk.
All right. Can you hear me? Can you see my screen?
Yeah, all good.
Okay. Well, yeah, thanks for the introduction. Hi, everyone. Thanks for joining this session. I'm Johan, and I'm a member of the Cache Lab. And today I will walk you through how we can visualize speedups from Cache using a Grafana dashboard. And this is part of our SIGCOMM'25 tutorial on networking for Stateful LLM Inference. And I will be focusing on the monitoring and visualization aspect, essentially how to take all the performance benefits from LLM Cache and make them visible in real time. And you will see how we set up the environment, deploy VIM with LLM Cache, and then connect everything together with Prometheus and Grafana to track metrics like latency, throughput, and token speed. Let's get started. One sec. Yeah, so here's the roadmap for this section. We'll start by launching the proxy server. That's what let us forward traffic and collect metrics. Then we will move to the VRM deployment with LM Cache using Helm and a YAML configuration file. Next, we will bring up Grafana and Prometheus so we can visualize metrics in a live dashboard. After that, we will run a benchmark to actually generate load against the model. And finally, we will switch back to Grafana and see those metrics line up in real time. Things like the metrics we mentioned before. And so by the end, you have seen the full pipeline from deployment to benchmarking to visualizations. Okay, let's just watch this video really quick, and I will commentate this video. Yeah, so we will start launching the proxy server. That's like what let us forward the traffic and collect metrics. Then so we just bring the proxy up step by step, exactly what you will see, what you just see in the clip. And in short, the proxy let us both route, request and collect metrics we will visualize later in Grafana. And first, I run the UV command Python 3.12 to create environments. And this create the Python 3.12 virtual environment. And quick side, if you are not familiar with UV, it's just a modern, faster replacement for the regular pip. And it's ROS powered, and it's much faster. Then we activate the environment. From there on, we just work under this environment. And then we installed a few dependencies we need, and Fast API for async web framework for the proxy, and a UVcorn HTVX and Prometheus client expose metrics for scraping. Then we go into the proxy server folder and run the Python proxy.py to launch the proxy. And here we can see the backend URL points the proxy data. The VIM router we forwarded to localhost 381 here with these flags, and port 8001 is where the proxy itself listen. And we can see the logs, and we see the backend connectivity looks good, and applications are complete, which means Fast API app is ready, and UVcorn is running on 8001, and the proxy is live and listening. And so we go to the just give you a look. This will be published after this talk, and you can see on the README of this Fast API proxy server README, I mean, if you prefer not to run it by hand, you can also use the helper script we show in the repo here. So you can run it by running like batch proxy control .sh to spin out multiple proxy instances, each of its own port, and it's wired to three backends: the in-cluster VIM router, Fireworks, Deep Infra for baselines on 8001, 8002, and 8003 ports. And in our demo, I just run. It's very similar to this one, but like with different backend. So we just launch a single proxy manually with Python proxy.py. So you could clearly see and control the flags using the backend URL flags and port flags. And just very briefly on Prometheus. So the proxy exposes metrics in Prometheus format. So including time to first token, request duration second, which is end-to-end delay, and plus decoding throughput and input output QPS. So we wire those into Grafana next to visualize the LM cache speedups. And let's move to the next slide. Yes. Yeah, I guess before we even run anything or like see the seed clips, let's pause to see this YAML file a little bit. So this file is called the CPU offloading YAML file, and it's what we pass into the Helm to configure our deployment. And if you're not familiar with Helm, it's basically a package managed for Kubernetes. So instead of writing raw kubes control commands, Helm lets us describe the configuration in one place and deploy everything as a reusable chart. So this YAML is telling Helm exactly how we want the VRM service to run inside our cluster. So now let's look inside the file. Under the service engine spec, we can see we just so we define the model to name Llama 3, and then we point to the container image repository cache VRM OpenAI latest, which includes VRM plus our cache extensions. And the model we are using is Hugging Face MetaLlama Llama 3.1 AB instruct. And we asked for one replica with resource requests of 10 CPUs and 40 GB of RAM and one GPU. And under the VRM config, you will see we set the max model length to 32,000. That means this engine will support context length up to 32K tokens. And finally, under LM cache config, we explicitly enable LM cache, which is here, and set a CPU offloading buffer size to 200 gigabytes. And that's the knob tells VRM how much KV cache can spill to CPU memory instead of just get evicted if GPU is full. And of course, there's a Hugging Face token at the bottom. This one's a fake one, but it's easy to get one. Just sign up, and then a request one is free. And we need to use this Hugging Face to pull the model weights from Hugging Face. So in short, this YAML file is the recipe for Helm. It specifies which model to run, how many resources to request, and how LM cache should be configured with CPU offloading. So now let's run it, or like let's watch this rest of this video. This video is not speed up, so everyone can feel like the actual speed of how this will be deployed. Yeah, this is the YAML file. Then we will go to the command line. Yeah, so I just start with the Helm install and I apply the YAML file to the cluster, and right away we will see deployed here, status deployed. Yeah, just checking the status. Yeah, so I just run kubectl get pod shows two pods. One is for the router and one is for the Llama 3 model. And at first they are container creating or pending, but like after a few seconds they both move into running. So now we can stream the model logs. you'll see where you see VRM is starting up, just like regular, it detects CUDA, detects the model, and confirms the model is 32K. We set up the YAML file. Yeah, I will just pause a little bit here so we can where is it? Oh yeah, it is. We can see the LLM cache configuration. We set up the CPU size we set up earlier, 200 gigabytes. Yeah, a lot of lines here are very variables, internal usage, context, KV, connected initialization. But I mean, the important takeaway here is the LLM cache is active and managing how cache will move between GPU and CPU. And yeah, next, the engine, we're just waiting the model to download and load it. It will take some time, but I just find people should like experience this whole process to see like how much time we should actually have here. Just not speed up this video. Yeah, we need wait a little bit for the model to be download and load. And we wait a little bit up here, and then and now the engine start downloading and loading the model. You can see here. You will see the progress bars here for the 4 safe tensor shards. Then a message saying the weight's loaded like about how many seconds? Like 120 seconds. After WIM runs torch compile and capture CUDA graphs, and which will speed up the later subsequent inference runs. And
there is a question, sorry for interrupting, but there is a question in the chat, like, can we track prefix KV cache migration event?
wait, sorry, I cannot see the questions.
You can click on the chat.
Yeah, one sec. Wait, oh, I saw it. Do you want to answer this question, Yuhan?
Yeah, so for KV cache migration, I assume it's like KV cache offloading or loading, right? Yeah, so there are some logs in the Allen cache in the BLM server side. Like for example, like it will say something like Allen cache has stored how many tokens out of all the tokens, and it retrieved how many tokens from the CPU backend to the back to GPU, something like that. It will show on the BLM server side. Yeah, Johan, can you continue the play of the video, and it will go to you can see the log like in the end. Yeah, so here it's like
Oh,
maybe
sure.
a bit afterwards. Yeah,
It,
afterwards when we submit a curl request to the server. Uh,
uh,
uh
is
like
it?
later.
Yeah, is it
Oh, it's not.
it's
Maybe
next?
it's not.
It's
Yeah,
next one, right?
it's not in this video, but let me share. Can you let me share the screen?
Yeah, I will stop share for a bit.
Yeah. Okay. Let me find them. Yeah. Okay. Yeah. So if you look at this video, and Yeah, so here on the left panel, like once you submit the curl request to the model, then you can see that it's saying like storing KV cache for 31 out of 31 tokens. And after it's done, the log will show like stored 31 out of total 31 tokens. And also, if when you submit another request, and if it finds the KV cache for the 31 tokens is inside the KV cache backend, then it will show like retrieve 31 out of 31 tokens. Yeah. Does that answer the question? Okay, nice.
Okay,
Yeah,
great.
Zhonghan, you can continue.
All right. Yeah, so finally you will see let me just put it here. Yes. So you will see API server comes online, you will see it listening on port 8000 and printing out all the available endpoints. Like we want completion, we want check completions. And at this point, the service is ready to take inference request with LM cache and CPU offloading fully enabled. And finally, once the pods are running and the API service live, we need a way to reach it from our local machine. So let's finish the rest of the video. And so here I run CTL port forward. So this tells Kubernetes to forward traffic from localhost port 381 to the VRM router service inside the cluster, which is listening on port 8000. So for now, so you can see. So yeah, so for now, whenever I send a request to localhost 381, it gets forwarded directly into the running VRM service on port 8000 inside the cluster. That's how the proxy and Prometheus scrapers will connect to it in the next steps. So you can see the confirmation lines here, the 2 lines. And yeah, at this point, everything is wired up and the model is deployed. Cache is enabled and traffic from our tools flow through these 40 ports. And now let's bring up the Grafana and Prometheus. Next one. Yes, it's a short video. Let's finish before I can commentate on this. Okay. So now that the proxy and VRM are running, the last piece is to bring up Grafana and Prometheus so we can actually visualize the metrics. So here I go into the Grafana folder and run bash start.sh to start. And the script uses Docker Compose to launch both Grafana and Prometheus together. And you might notice yeah, I mean the small one you can ignore. Then you will see the confirmation the Docker network is created, and both the containers Grafana and Prometheus are started successfully here. Once the containers are up, Grafana exposes its web interface on port 3000. Here you will see me. Here you will see me forwarding the. So here you will see me that forward the port to localhost 3000. And that means we can open a browser and connect to the Grafana dashboard directly. And there's the Grafana UI. I think that's the end of the video. Yeah. And this is the LLM monitor dashboard we prepare. And at the top, we have panels showing query per seconds, input length, and output length, and estimated cost per 100 million tokens. So below that, we have metrics like time to first token, average request duration, and average generation speed in tokens per second. And on the right, you will see a live chart or request throughput over time. And right now, the panel says no data because we haven't sent any requests yet. But once we run inference workload through the proxy, Prometheus will scrape the metrics and Grafana will start plotting real numbers. And that's how we will visualize speedups. And we can also compare baselines versus LM cache here. And then we can start benchmark so we can actually see something on this dashboard. So yeah, so let's kick off the load so Grafana has something to plot. And so yeah, so we'll move into the no, this is oh yeah, this is the correct one. Okay, so we're moving to this synthetic folder, which has a bunch of baseline, benchmark, or like traffic generation you can run. And yeah, first we need to install several dependencies. Yeah, so I just started the benchmark by running this run inference.sh bash file, and you will see the first line running benchmark QPS equal to 6. So which means we try to cap about 6 requests per second. Did it skip the? Yeah, so it will first you will see so we will first warm up the engine here. You can see it warm up the engine, and then because these are voice penalizing the first few requests while kernels compile and catches few. Right after that, it says start async loop and awaiting 10 tags to finish, and then when we finish, we can actually start sending requests. And as the loop stabilize, the script begins to create actual like synthetic users. You will see line like adding users. So basically now it's sending requests to the server, and now we're actually processing the request. And at this point, Prometheus is scraping the proxies metrics, and Grafana will begin to populate the metrics. And if you see that if you go back to the dashboard now, the no data placeholders will flip to real values, and the request processing speed line chart will start to climb. And I mean, two quick tips. I mean, when you run these things by yourself, I mean, if you need more activities, you can just bump the QPS in the script and rerun. And if the GPU looks saturated, like very saturated, just dial it down to keep the P95 latency reasonable. And I mean, you can also adjust the prompt length and output length if you want. And we will let this run a little bit, and then we will switch to Grafana and compare the baselines. Just the next slide. Yes, which is this one. So let's take a look at the live Grafana dashboard. This is and then at the top left on this dashboard, we can see the input and output length we use for the benchmark, which is 20K input token and 100 output, and that's a pretty challenging setup. So it's really stressed the system. And if we move to the right, the dashboard compare the cost per 100 million tokens across 3 backends, our systems, Fireworks, and Deep Infra. And we can see that ours is below $1, while Fireworks over $6, and Deep Infra is close to $3. And down below, we can compare latencies. The time to first token is less than 1 second on our system, like around 0.55 seconds. And while Fireworks and Deep Infra takes more than 10 seconds. And similarly, request latency is only about 3 seconds compared to over 22 seconds for Fireworks and about 90 seconds for Deep Infra. And on the left bottom panel, you can see the generation speed. We are generating around 51 tokens per second, while it's about 10 times faster than Fireworks and several times faster than Deep Infra. And finally, on the bottom right, you can see the request processing speed graph shows throughput over time. And the green line, which is our system, is sustaining roughly double the request per second compared to the other two other two services. So overall, the dashboard makes it very clear. I think it's very cool too. Our system is consistently faster and cheaper and more efficient than the baselines. But it's just a very cool dashboard, and then easy to understand, easy to visualize. Oh, I thought there's a questions. Okay. Yeah, it's in a stable loop, so it will pretty much look the same, and you can see. Yes. So yeah, this actually wraps up the demo, and thanks all for following along. And I hope this give you like a clear picture of how LM Cache integrates with VRM and how we can actually monitor the speed ups live in Grafana. And if you'd like to dig deeper or try this out yourself, which I highly recommend, we've made everything available on GitHub. The code of how to launch the proxy and run benchmark will be public after we will make open source after this talk. And again, I mean, you can check out the LM Cache repo, the demo baseline benchmark repo after the talk, which include the full code and script we presented today, and also the VRM production stack, which include a tutorial on how to deploy VRM plus LM Cache using Helm. And I have added links and QR codes. This one will be published after the talk, and you can jump right into the other two. And of course, I mean, feel free to reach out to me or Johan if you have any further questions. And then we'd love to hear your feedback and what you build with Cache. I think, Johan, that's all I have today.
Okay, thanks, Rohan, for giving the great talk. Yeah, there's a question in the chat, like how the cost per 1 million tokens is calculated. From the QPS, it seems that the Ion Cache improvement versus fireworks is 2x, but the cost is 6x. Yeah, so the cost is actually calculated with like the request processing speed and the cost of the GPU per hour. And the reason why Fireworks has like Ion Cache has more cost saving like than what the QPS than the request processing speed seems is like the Fireworks GPU is GPU cost per hour is higher than what Ion Cache uses Ion Cache like the deployment GPU cost uses. Yeah, so that makes like the improvement even more in terms of cost. Does that answer the question?
Yeah, thank you for the answer. Yeah.
Okay, thanks for the question.
Yeah, thank you.
Are there more questions from the audience? Okay, yeah, so just a quick note that the code repo Johan presented, the demo benchmark code will be open sourced after the talk. Yeah, we are waiting for the repo owner to open to publish the repo. Yeah. Okay. If there are no more questions, our next session will be 15 minutes in 15 minutes. So yeah, let's take a short break before the next session.
Thank you, Johan.
Thanks, Johan. Which is the best glue layer between the inference engine and the infrastructure and the VLM production stack, the most performant production level deployment under the hood of VLM projects. Okay. Yeah, Kuntai, you can start the talk and yeah, start sharing your screen. Oh, you're muted, Kuntai.
Oh, yeah. Let me share my screen. Okay. And to share the screen, I can find. Yeah. Can you guys see my screen now? Is it
Yeah.
visible?
Yes,
Okay.
it is.
So yeah, I see. Okay. So after this talk, you will learn about like the integration process, like from my perspective, and you'll learn like the lessons that I learned and the failure that I like the errors that I made. And hopefully it's like it also like, hopefully it also inspire you on building the integration with open source project. Yeah. And the first question I want to like just confirm is that why am I using my perspective of like illustrating this integration? There are three reasons. So the very first reason is that me personally have close connection with both VLM team and IM Cache team. And the reason is that I visited UC Berkeley and worked with VLM team for more than 1 year. And yeah, and this gives me like enough like insider view of both VLM and IM Cache and how the integration works, so that I can give you a more comprehensive picture of this whole integration process. And the second reason will be I proposed and drove the open source VLM and Memcache integration so that the engineering are designed and done like by me and by our team, so that like we are the first-hand engineer that actually resolves all the nitty-gritty details inside. And the third part is because the process of developing the design will give you much more insights than just describing the design itself. Yeah, and this is also partially like why people write research papers about their system, because the thinking process of developing the design is more important than it's not always more important, but it can be more important than the system itself. Yeah, okay. And before diving into the integration, I want to just remind people of the basics of LLM inference. I guess maybe you guys already see this, but I just want to reiterate on this so that we are on the same page. So first, LLM inference is basically separated into two stages. The first stage is prefill stage. The prefill stage will read the input and generate one output token. And in this example, like the input will be this is tomato a fruit, and the prefill stage will read all tokens inside is tomato a fruit, and then generate one output token. In this example, it. And then in the decoding phase, it will generate one more token based on already existing output tokens. So in this example, it will run the inference again and generate one token is. And we can see that in this figure, there's like a thing called KV cache. Basically, KV cache caches the previous commutation from the prefix. For example, like the KV cache over here, the iteration 2, it caches the commutation of is tomato a fruit. Yeah. And so that's the basic of our inference. And then we can start about the real topic. So before diving into the whole integration, like let's start by the main use cases of IM Cache. Basically, it's the use case that drives the integration. So currently, the use cases of IM Cache is mainly twofold. The first part will be prefill decode disaggregation. Oh, and the second part will be prefix caching and KV cache offloading. So the first one will be prefill decode disaggregation. Uh, this is a like last year's OSDI paper, if I remember correctly. So basically, this technique was introduced from there, and the motivation is like the industry people spend a lot of time to trying to figure out the motivation, and there are two things. The main motivations are two things. First is that it resolves the bumpy inter-token latency issue. So without PD disaggregation, there will be interleaved prefill and decode. And as we already said, the prefill stage will read all the tokens and generate just one token, but the decode stage will just generate one extra token. So basically, the prefill stage is doing more work because it needs to read all the input tokens. And in this stage, it will interleave between prefill and decode. The prefill stage will slow down. Like the prefill stage will basically separate the decode of like maybe one existing request. It will separate the decoding stage of those one request because the prefill is just injected in the in between. And in that case, you will observe that the output token suddenly has a very long latency, and that was the initial behavior of ChatGPT. Yeah. So basically, there's a bumpy inter-token latency issue that is really hurting the people's like users QoE, quality of experience. And the second reason is that, which is actually the major reason that people are using PD disaggregation nowadays, is because PD disaggregation can decouple the parallelization strategy between prefill and decode. And as a background, since prefill is reading all the input tokens, it's reading a lot of things. So prefill is commutation bound. And the decode, it will just generate one more extra token. So it's typically memory bound. In that case, because prefill and decode are bounded by different resources in GPU, we want to place them on different hardwares and customize them so that it will maximally leverage the hardware capacity. So for example, maybe in prefill you want to use depending on SLO, of course, but for prefill, maybe typically you will use a hardware that is better in computation. And for decode, maybe people prefer a GPU with higher memory capacity so that you can fit all the requests inside it to maximally batch the request to maximally utilize your GPU memory. And yeah, that is the main motivation of this technique, prefill decode disaggregation. You can see the OSDI paper like for more details of this technique. Yeah, and the second use case will be the KV cache offloading. So basically, KV cache offloading, it persists the KV cache so that it can potentially be shared by other requests if the other request happens to have the same prefix as this request. So this is most people think that prompts like the requests are just like difference between users pretty random. Like maybe this sharing doesn't help much, but actually in large language model applications, this is a very important optimization because like there are several common patterns that are exactly making the requests sharing the same prefix. So for example, I'm not sure if you guys know, but ChatGPT has a very long system prompt. So it will write about like maybe 4,000 words at the very beginning of every request to just guide GPT to be helpful and to generate the right behavior and to tell it how to use the various tools, etc., etc. So this system prompt is shared across all requests as a prefix. And it's a very ideal use case for prefix caching because we don't want to process the system prompt again and again. Yeah. And the second use case of KV cache, this prefix caching, is multi-turn conversation. In multi-turn conversation, people just chat with the large language models again, and again. And in each chatting it is like appending the new chatting history to the already exist old chatting history so that it naturally grows, like the chat history naturally grows with the user interaction. And every growth, you can use the commutation of like every growth will result in the old history will make the old history a prefix. And in that case, we can use prefix caching to accelerate the commutation. And the third example would be the long document query. So, for example, imagine that your company has a lot of internal documents, and while multiple people are querying about the same document, we do not want to process the same document again and again. In that case, we can make this long document a prefix, and then we can share the commutation between different users. And yeah, so basically, previously means that maybe before the start of this year, people think that GPU will be more than enough to store all the KV caches. Yeah, but recently, the KV caches is becoming larger and larger, and is exceeding the capacity of the GPU itself, and it's because of multiple reasons. Here, I'm putting two reasons here. So basically, the first reason is that because the inference time scaling trend. So basically, in inference time, like a large language model will do more things than just outputting the tokens. It will think, and that thinking process will generate a lot of tokens that can also be prefix cached, and which in this case will make the KV cache size grows larger because it thinks more and it has more extra tokens. And Another trend is that people are nowadays using longer context models. So for example, the latest open source model, GPT-OSS, which is open source by OpenAI, that model has a very long context length. If I remember correctly, it should be like 128K. And in that range of context length, people can basically, for example, if you're doing a coding application, you can basically stuff all your codes inside the context window and let it generate the new results. So because the model's context is getting larger and larger, people start to abuse it, and this will result in a larger and larger KV caches, where KV cache is basically a state that grows linearly with respect to the input length. Yeah, and let's talk about it. Now we can start about the implementation. So basically, the prefill decode disaggregation, this technique starts earlier. So let's start with that. And before my effort, previous PD disaggregation implementation all failed to merge into the open source repo. And it's basically because at a high level, they are doing this thing. So basically, the um, the VLM, it will has multiple components: scheduler, worker, KV cache manager. And the scheduler basically schedules the request. Worker just execute them in GPU. KV cache manager do the memory management, which is the key technique of VLM. And they are using this kind of implementation where they duplicate the components inside VLM to the prefill copy and decode copy. For example, it will have prefill scheduler, prefill worker, prefill KV cache manager, and this should be decode. Sorry for the typo. And the right side will be the decode scheduler, decode worker, decode KV cache manager. And this duplication, basically, you can imagine that to duplicate these two things, you need to write a lot of glue code. And the issue will be the code footprint will be really large. So for example, in this implementation, it occupies like over 2,000 line of code. And this is a real PR. This is like an internal PR originally developed by a company. And fortunately, I'm fortunate to see their PR. And yeah, I literally counted the code, and it's a lot. Yeah. So basically, this kind of implementation is like they are choosing this implementation because it kind of like feel natural to the engineers. And why is that? Because PD disaggregation, you can treat it as a parallelization technique. And in traditional machine learning, the parallelization technique such as tensor parallel has a pretty like good implementation. Basically, in this example, like people will basically create multiple tensor parallel rank 1 and rank 2 and let them share the scheduler, but they will have different worker on different nodes, and they'll have different KV manager on different nodes. And so basically the previous implementation, which is this one, basically follows the paradigm of this implementation. But this implementation is not good for prefill decode disaggregation, and I'll argue for that. So basically, in traditional tensor parallel, it has a very tightly coupled control loop. So in tensor parallel, there's like the communication is called all-reduced communication. All-reduced communication is happening after every layer, every MLP layer. So like for large language models, a typical model will have like 30-ish layers, and a larger model will have even more. So basically, it has a very frequent synchronization between just even one forward path. And the communication is a blocking communication, which means that the engine cannot further proceed if the communication is not finished yet. But in prefill decode disaggregation, the control loop is loosely coupled. So basically, the communication only happens once per request. So basically, it only happens between the transition from prefill to decode. And it like the previous communication, it will happen like maybe even 1,000 times of one request. But this communication, PD disaggregation, will only happen once per request. And secondly, it's a non-blocking communication, which means that you can still run other requests while like doing the communication and transferring the KV cache. So such a contrast between tightly coupled and loosely coupled, it basically like this implementation this implementation, it basically it will let it has a, like a, it's more like a centralized control. And centralized control is better for a tightly coupled implementation. But since we found that the PD desegregation is a loosely coupled control loop, we like my implementation was switched to a different way. But basically, instead of controlling everything inside of one single VLM instance, I basically forked VLM itself into two copies. One is prefill VLM, one is a decode VLM, and I'm communicating them. And then I build communication between these two instances so that they can communicate with each other. So basically, by doing this, I'm emphasizing that they are actually only loosely coupled, so that if they're just loosely coupled, why not just putting them into two different, why not letting them have separate logic and having separate control and having like completely separate instances? So that's why I'm building this implementation. And I'll give a high-level description of what I'm building. So basically, I'm introducing a new entity, which is the middle part. It's called KV cache connector. I'll call it connector for short. So basically, it behaves like a WebSocket. And implementation-wise, I wrap around the previous stage of the VM engine. So basically, before the prefill GPU execution, for prefill node, I'll do nothing because I want to do prefill. But for decode code, but for decode node, I will receive the KV caches from the connector, skip the prefill. And after prefill GPU execution, for prefill node, I'll send the KV caches to the connector and skip prefill. But for decode node, I will just do nothing because it still needs to do decode. Like previously, we're all talking about PD disaggregation, but actually it turns out to be highly related to IOM cache because this implementation of prefill decode disaggregation can also be used for like KV cache offloading, which is the second use case of IOM cache. No, it's not, sorry, it's the initial use case of IOM cache, and PD deseg turns out to be second use case. And it's like, yeah. So the sharing the ability to be able to share the implementation between prefill decode deseg and the KV cache offloading, it is not a coincidence. So the reason is that both KV cache offloading and PD disaggregation, they need to transfer the KV cache across IAM instances, and this is a common characteristic. And it's not that it happens to be the KV cache that needs to be transferred between different engine, and there's a more deeper reason behind this. So basically, it is because that the KV caches describes the state of the computation, so that you need to transfer the state of the computation between inference engine to overlay their computation, it's like your yeah. So basically, you want to like overlay the you want the another inference engine to continue computation of a of the previous results, whether it's prefill or it's like previously calculated KV cache. As long as we want to continue the computation, we have to transfer the computation. We have to transfer the state of the computation, and that state is KV cache. So this is like a commonly shared like networking wisdom. Like you need to build like in networking, we always want to build a very efficient communication library to transfer the state of for the computation, like whether it's cache or it's like other intermediate states. Yeah. And the overall, like here is a more detailed like the workflow of this implementation. So basically, there will be a prefill node and decode node, a prefill VLM and decode VLM, but then it will be an orchestration logic on top of it to orchestrate the communication patterns. And this starts to look like microservice, but it's kind of very similar. So basically, this proxy API server for incoming request, it will set the max token equals to 1 first. This max token means that how many tokens this engine is allowed to output. And since prefill just output 1 token, we just set it to 1 to let it do prefill. And then we send it to VM prefill engine, and it will receive the request and do the prefill. But after the prefill, it will call API called buffer. It will buffer the KV cache into a KV cache transfer thread. and then it will generate the first token and return the first token to the proxy API server. Then the proxy API server knows that prefill is done. It will then send a request to VM decoding instance using this original max tokens. And then the VM decoding instance will receive the request, and then it will call a new API called drop select. It will basically select the KV cache from this KV cache transfer thread and then drop it. And then it will use this API to get the KV cache and skip the prefill. And then it will, and then because of implementation limitation, it will still generate the first token again. Yeah, and it will return to it will then return the first token to the user, and then it will generate a second token, a third token, and on forth. Yeah, and yeah, I saw a question here, but basically the question is, does Memcache offload the prefix KV cache directly after prefill phase ends, or once the GPU HBM is full? Good question. So basically, the current implementation of Memcache is called copy-based offloading, which is where it basically copy the KV cache from in GPU and offload it to the CPU. So in this case, in this copy-based offloading paradigm, it will copy the KV cache right after the preview ends. But we're also working on the eviction-based offloading, or you can call it like zero copy offloading, where we only copy the KV cache once GPU is full. So this implementation is ongoing, and it's a very important implementation because in the latest hardwares, the GPU memory is on par. The GPU memory size is on par with CPU memory. So if we are copying data, we are basically losing half. Because we're copying data, we will duplicate the KV cache inside the GPU onto CPU, and in the case where the GPU CPU memory is on par, it's not good. It will reduce your total available memory by half. So yeah, we are still working on it. Okay, and feel free to type any questions, and I will check them like inside some slides. Okay, and this implementation is pretty good, and we happily use this API until VM v1. So VM v1 is basically like VM v1 is like a major change to VM, and it's changing it for a good reason. So basically, it's like all softwares will have like periodic refactor, and the same story for VLM software. And the reason is that VLM community did a very great job of scaling the project horizontally, including a wide range of models, including tons of features, and including very diverse hardware backends. And to just enumerate a few, so basically, VLM will cover NVIDIA GPU, of course, but also customer side, consumer side GPUs like RTX 4090, and also it will cover Google TPU, it will cover AMD GPU, and it will also cover OpenVINO, which is a Intel CPU backend, and it also covers some customized hardwares from multiple companies. Yeah, so it's a very diverse hardware, and because of like it scales so fast, it it has a cost where the cost is that the compatibility between features is very poor. So basically, these features were developed separately by each other, and so it's very difficult to combine optimizations A plus B plus C plus D for models X, Y, Z. So basically, combination is becoming very difficult. Just to give a very simple example. So for example, preface caching, this feature sounds trivial, but once the model is like multimodality model, it's much more difficult to do it because in multimodality model, the index of the KV cache is no longer just text, just plain text or equivalently tokens. It will instead becomes the intermediate features. And these intermediate features is very difficult to hash and it's very difficult to index. And in that case, it makes the previous caching a lot more challenging. And the second reason is that over the past 1.5 year of VM, it has accumulated a lot of technical debts. And basically, to rush for the model implementation, there's a lot of hacky ways of doing that. And I can raise a lot of examples, but yeah, long story short, basically rushing for the model production deadlines to shoot for the day one support of models. And that is very important, but that accumulates a lot of technical debts. And it makes the code very difficult to maintain. And so basically, it's very hard to implement new features. Once you change code at place A, and it will mysteriously crash another feature that you never know before at place B. And fixing them is very tedious. Yeah. So basically, this via V1 will the goal of your V1, which is basically the goal is to improve the scalability and to improve the feature compatibility and to remove the code, to clean up the code. And how does it do it? It basically introduces two new things. The first new thing is called Simplify Scheduler. And the key thing it does is it uses chunk preview by default. So basically, I'm not sure if you guys know chunk preview. I'll quickly run through an example here. So basically, chunk preview, it will preview only n tokens at a time. And this n is a configurable value, and this example is 10. So basically, we can see that this request R1 has 3 tokens, R2 has like 5 tokens, R3 has 10 tokens. So that in step 0, we will schedule 10 tokens at a total, and we'll go through the order of R1, R2, and R3. R1 3 tokens all scheduled, R2 5 tokens all scheduled, R3 we only have 2 tokens remaining, so that we only schedule these tokens. And for step 1, like because R1, R2, the input tokens are all scheduled, we can schedule one more token for the decoding. And for R3, we can schedule remaining tokens. Yeah. And then for step 2, we schedule R1, R2 for its decoding, which is 1 token. We schedule R3 for the last prefill token and one decode token. And for step 3, we schedule the decode token of all requests. So that basically in this kind of scenario, we can see that, for example, this batch here, like for these 2 requests, it is in decode phase. But for this request, it's in prefill phase. Basically, in this kind of in this chunk prefill based technique, there will be no longer a clear separation between prefill and decode. And that leads to the first engineering challenge, which is which will introduce like performance degradation. It's not straightforward, but like let me try to explain. So basically, vanilla VLM needs multiple scheduling steps to finish preview. Basically, because of this chunking mechanism, it needs to have multiple steps to finish a preview. And since, like for example, if you're having a chunk size of 1024, we can finish like a 10,000 token request in 10 steps. The preview of it, we can finish in 10 steps. But since like previously, like ideally, we want to just skip these 10 steps and directly jump to the decode phase of this request. But this is not doable because each step now contains other requests. And we still want to do the decoding of other requests so that it cannot be easily skipped. And the result is that even though these, like for example, for this request, even though we already finished the preview of these 10,000 tokens, we still need to wait for 10 extra steps just to let other requests finish, just to run other requests normally, and then we can switch back to this request. And this will result in a performance degradation because you need to wait for 10 steps for this request to even start the decoding, even though the preview is already done. And these 10 steps accounts for like hundreds of milliseconds. And so it's a long time. Imagine that you're waiting for a ChatGPT for almost 1 second. It's not very ideal. Yeah. So this is the first challenge, and which is a performance degradation. The second challenge is because a lot of features need to be supported. And here I'm copy pasting the slides from VLM team, and you can see that here's a whole bunch of features: model supports, hardware supports, performance, production features, re-architecture, open source community, all bunch of things. It will result in a these all bunch of things needs to be compatible with our preferred decode disaggregation implementation. and the compatibility is not easy. And the original implementation that I mentioned, like maybe several slides earlier, which is here, this implementation is not compatible with a lot of features. For example, CUDA graph, speculative decoding, chunk preview, multimodality, and more. So um, I want to quickly introduce CUDA graph because it's dependent on it's like the dependency of following slides. But other techniques, you can still take a look at it. If you're interested, you can search for it. And those are all very important optimizations for large language models. So CUDA graph is a technique that basically it will allow the CPU to launch a sequence of kernel instead of just one single CUDA kernel. And because the kernel launching process, it takes milliseconds, it's millisecond level. So in that case, we do not want the CPU to frequently launch a lot of kernels because launching itself is a slow operation. So instead, we want to launch the kernel we want to directly launch a sequence of kernels. And this technique of launching a sequence of kernels is called CUDA graph. Okay, and yeah, just recall we have two challenges. One is that we have performance degradation because of in the over implementation, and we also have feature incompatibility, and this can be like we have like VRM raised very like two innovative engineering effort to resolve these two challenges. The first insight is that the KV cache related operation are all attention operations. So basically, attention operation like the KV cache, the K and V stands for key and value for attention. So basically, it's only related to attention operation, and basically, the attention operation are in the new V1 V1 is now isolated. It's now isolated. It's like exposed outside the compilation of CUDA graph. So basically, there's a new technique called piecewise CUDA graph, where the like previously entire model are captured in the CUDA graph, where because it's all captured in CUDA graph, it's not very easy to modify it. But now we are using like VRM is using a hybrid approach, where only the attention operation are executed in eager mode. Eager mode meaning that it's executed in a synchronous manner, where each operation you can directly see the results. There's no, and you can modify it on the fly, and it will put the attention operation in eager mode. But other operations like the linear operation, basically all the linear operations into like the CUDA graph. So this is doable because the CUDA graph technique mainly benefits non-attention operations. So CUDA graph has the most performance gain on non-attention operations. So it's okay to expose the attention operation to expose the attention operator into native Python, which means that you can edit it. It's like executed in eager mode, and it's okay because the overhead of doing so is not very large. Yeah. And the second insight of solving these two challenges, which is the second challenge is compatibility challenge. To solve the compatibility challenge, we identify an important API called prefix caching API. And this prefix caching API is actually isolating the feature implementation and the underlying KV cache management. So basically, here is a small illustration of this figure. So basically, the computation state management, which is the KV cache management, is isolated into a separate module. And this module is communicating with other feature implementation using this prefix caching API. And since we have a nice separation of this like feature implementation and the KV cache management, as long as we make our implementation compatible with this prefix caching API, we can make it compatible with other features. And these other features are tons of features, a wide set of features, multimodality, speculative decoding, and the structured decoding, and yeah, all kinds of optimizations are kind of like encapsulated inside this prefix caching API. Okay, so to incorporate those two changes, to incorporate these two insights, we have like our solution will be like this. So basically, we will have a scheduler. We will schedule the KV cache transfer under the hood of prefix caching. This results in a scheduler side API of our implementation. And then we execute the KV cache transfer inside the attention operation. Basically, this is enabled by the piecewise product graph technique. And this results in our GPU worker side API. And this scheduler executor separation is an old wisdom of networking community, which at a high level is basically control plane and data plane separation. So you control the data movement first and then really execute it. So control first and then execute it. And this will also result in like basically re-leveraging this old wisdom also give us a much more better implementation. Okay, and so basically, let's talk about the connected APIs that we're currently building. And for this part, I guess the best way to do it is to check the code and to go through a code real quick, so that I'm having this like code for you guys to see. So let me share my screen again for the code. Yeah, okay. And this is under the VM current main branch, and so basically it has multiple APIs, and here we have a worker side methods, and the first several methods are a lot more like metadata binding. The real thing are here. So the first API is, let me zoom in. The first worker side API is basically GPU worker, and it basically executes the KV cache transfer. So here we expose multiple synchronization points. One is a start load KV, and this is executed before every layer forwarding. So basically, upon layer forwarding, upon the forwarding of one layer, it will call this API for you to synchronize your computation because we want to load data first and then compute. So this ensures the synchronization. Similarly, here there's a API for you to here's an API for you to like wait explicitly request a wait for the KV cache to finish loading. And this is important for the correctness because without any wait, there might be data corruption, and it will result in a wrong forwarding result. And this is a KV cache. This is a layer-wise KV cache saving API. So basically, it allows you to save the KV cache into the connector. It will give you the KV cache as a tensor, and it will give a lot of useful metadata in this attention metadata for you to save the KV cache. And it will also have a synchronization for you to wait for the save to be complete. And there will be also several management APIs. For example, here this get finished. It will get the finished state of the request to wait until it's finished, and it will return a lot of like useful metadata inside the request. And yeah, this is just for simple shutdown. Scheduler side method, since we're operating with prefix caching, so we are having this API called get non-new match tokens, where basically we are trying to check how many extra prefix tokens we can hit from our simple connect from our connector, and this is exactly designed based on prefix caching. And the second thing will be update the state of allocation. So basically, it's because we want to plan the KV cache transfer first and then execute it. This one does the plan part. This one does the planned part. Sorry, this one does the planned part of the execution. And it will also update the connect output. It will embed, because the scheduler and the worker are in different processes. This one will encapsulate all the instructions into an opaque object and transfer it to the worker side. And this one is for management. Yeah. Yeah. Okay. And yeah, I guess I'm slightly over time. I'll be real quick. Yeah. Okay. And the impact is that this API allow IAM cache to be used together with VLM without any VLM code modification. So there's no code modification. You just simply turn it on by using clear arcs or environment variables. And we're glad to see that other inference engine is started to follow up. For example, the TensorRT LLM from NVIDIA is following the same set of API as us, so that it can also support the Vibrate ecosystem brought by this connect API. And we are glad to see this many adoptions. And so a summary is that our vision is to build a socket for large language models using a series of syscalls. And we have a production-ready implementation of this paradigm where the inference engine is VLM, the syscall is KV connected API covered by this talk, and the socket is LLM cache. And we're happy to see these many adoptions. And that's all. Thank you.
Hey, thank you. Thank you, Kuntai, for the great talk. Hey, any questions? More questions from the audience? Okay, if not, now it's the lunch break, and the next session will be in like 1 hour and 5 minutes. So yeah, hope to see you guys then. Now let's have
Yeah,
a
see you.
break now. Thank you, Kuntai. Thank you, everyone.
Yeah, thank you, everyone.
Okay. networking for stateful LLM inference. Next session will be Yue Zhu. So Yue is a staff research scientist at IBM, specializing in foundation model systems and distributed storage systems. Yue obtained a PhD in computer science from Florida State University in 2021 and has consistently contributed to sustainability for foundation models and scalable and efficient storage solutions. Okay, Yuan, you may start sharing your slides and start
Sure.
talk.
Thanks for the introductions. Just give me 1 second. Let me try to share my screen. Okay, can you all see the screen?
Yeah.
Okay, thanks for the
Okay.
Yuhan for the introductions. So for today's presentations, I'm going to give the sharing the experience about running disaggregated preview with LM Cache. And I'm Yue Zhu from IBM Research. And so for today's presentations, it's mainly about my user experience sharing, and does not represent the IBM's views. And so let's get started. So to really get started about the exciting part, like let's take a step back. So for here is we're trying to give some examples and also some details about prefilling and decoding and why we need disaggregated PD. I think in the previous presentations, Quintai has already gave a lot of details about how LM Cache enabled all those features. But for here, we just gave some high-level overview to go through the main idea and also some backgrounds regarding the disaggregated PD. So over here, like when we try to run inferences on large language models, we have input prompts sending to the GPUs, and it's gonna generate a bunch of tokens. So this is not just a one uniform process. Actually, here we see there are two different phases. One is the prefill, and one is the decode. And these two phases, they behave quite differently on hardwares. So in the prefill phase, the model takes the input prompts, runs the forward pass, build up the KB caches, and this phase grows with the cost grows with the prompt length. So the longer the prompt it is, the heavier the prefill. And after the first token is ready, we move into the decode phase. So here, the model generates tokens one at a time, autoregressively. And also, we are reusing the KB cache here. So the decode is actually like more like a sequential, and the newly generated new tokens actually depends on all the previous ones. So like the figure we are showing here, like for the prefill and decode, like for the prefill is before the first token, the first output token appears, everything is the prefill. And once the first token is produced, and the rest of the sequence are for the decode. So traditionally, both prefill and decode may share the same GPU and the same symbol, like one machine, one workflow. But under the hood, and these two phases suggest the GPU in completely different ways. So the prefill here is computation bounded. It's stimulated by matrix multiplications. So the GPU's compute units are saturates, the flops utilization is high. And here is where exactly what the GPUs are great at. So for the decode, on the other hand, it's more like memory bandwidth bounded. As we mentioned on the previous slides, the newly generated token actually depends on the previously already generated token. So as the output grows, the models repeatedly reads or stores the KB cache to and from GPU memory, and the KB cache gets larger and larger. So the bottleneck shifts from the compute to the memory bandwidth. And at the same time, the GPU compute units may end up sitting idle and waiting for the data to arrive. So when we place these two phases together on the same GPU, so one is more compute intensive, which is the prefill, and other is the memory bandwidth or memory intensive. These two phases, they don't align very well. So this creates inefficiencies. For example, sometimes we may need actual prefill nodes for super long prompts, but the decoders, at the other hand, they may dominate the generation time if the generation load is high. So the flexibility of trying to scale the two-phase independently is only when we can put the prefill and the decode on different GPUs, and also that can help us also scale out across the nodes. For here, so instead of forcing prefill and decode to share the same GPU, we can try to decouple them, like what we mentioned. So by the disaggregation, we can run prefill on one set of GPUs and decode on another. So the prefill GPUs are kept busy with the computations, while the decode GPUs focus more on the memory-intensive token generations. And this avoids the interference between each other and give us opportunities to let each phase scale independently. So for here, like once we have the disaggregate prefill and decode, the key challenges become how do we move the KV cache between two phases more efficiently. So the first option is we have the direct data transfer between GPUs, and this fast path supported through the powerful Nixel library. And for using the Nixel library, it allows the inter-node GPU direct data transfer through the NVLink, or it also allows the direct data transfer across the nodes by leveraging the GPU direct RDMA. Of course, we can have like the KV cache being offloaded to the CPU memory or even to the SSD when the GPU memory is scarce. But of course, this gives us a higher penalty for the latency. But come to the slide, the main idea is saying that by having the Nixel support, we can move the KV cache both within the node or across the nodes. So this helps to have the disaggregated PD in the real practice. So for here, as we mentioned on the previous slides, that since we want to, or we have opportunities to scale the prefill and the decode differently, but once the KV cache needs to be across the nodes, the network dominates the performance. Traditionally, if we try to scale out, those traditional network does not have the direct support for GPU to GPU communications, and the traditional TCP/IP could add overheads by having those context switches, serialization, deserializations, etc. The RDMA here, which is the remote direct memory access, helps solve this gap. It bypasses the CPU, eliminates the kernel overheads, and enables the low latency, and also supports GPU to GPU data transfer. So let's look at how RDMA matters to the disaggregate PD. But before we directly jump into the demo, we are going to look at the LLM cache, the architecture at a very high level, to see how it supports Nixel-based KV transfer for the disaggregate PD. So for this slides, actually, thanks for the LLM cache teams. The original slides was from the presentations, LLM cache presentations in this year's Open Source Summit at North America. So basically, this slide shows the architectures of the LLM cache, but for here, we are trying to show the focus on how KV cache is transferred between the prefill and the decode in the disaggregated setup. So basically, the blue arrow here indicates that the KV caches, by having the Nixel support, the KV cache can be directly transferred between the two-way LLM instance. And for the other amazing features like auto-scalings, routings, feel free to refer to the LLM cache website for more details. And then we are going to show how we leverage the GPU direct RDMA for the disaggregated PD when we are using the LLM cache with production stack. So for here, it's like in the having the GDR support for disaggregate PD. So we basically let the decode pod to directly pull the KB cache from the prefill pod with the Nixel support. So here we list a few changes that are required to make this happen. So for the example, what we are showing here, actually we are using the Melta CI for the secondary network. And so for the annotation here, this actually indicates that the POS needs to pick up the secondary network through the Melta CI, and the McVLAN network here is the specific network attachment different definitions, and it's usually backed by the McVLAN CI plugin. And so by having this, this provides the POS to have the direct access to the high-speed network interface card. Probably it can go up to 100 Gbps or even higher. And this allows the pods to bypass the default slow Kubernetes network. And the second is for the security context, and this is to set up privilege on the pod. So we can grant the containers permissions to lock the memory using the mlock. And this is often required when we try to use CUDA or the UCX because it helps avoid the memory being swept to the disk. And RDMA here is the RDMA devices that we need to be assigned to the pods. And for the last portion is also the very important ones, that's the environment variable required for the UCX. The UCX is unified communications that libraries that use the underlayer the Nixel libraries. So by setting up the RC here, it helps the UCX library to pick up the RDMA for the underlying data transfer. And also the GDR copy here is actually for the small data transfer. These are the very important environment variables that we try to set up for the having the GDR support by using the Nixel for this demo. And so over here, going to the more details about this disaggregated PD demo, we are using the Kubernetes with the Helm chart provided on the production stack. So feel free to refer to the tutorial session for the disaggregated PD on the production stack. And for this setup and for this demo, we are only using one prefilled pod and one decode pod, and they put two separate nodes. But of course, right now, I think the LM cache has a very good support on the X, Y, and X, P, and YD for the disaggregated PD. But for this demo, we just use one prefill and one decode pod. And for the demo setup itself, we are trying to testing with the Llama 3.18 billion instructor models. And also for the benchmark results, benchmark script, we are using the VLLM benchmark serving scripts. And here we list out the environment variables that we use in the setups. So basically, we are using the random data sets with a long input prompt length, which is 8,000, and output token length is 200. And the number of prompts is 30, and the request rate is 1.1. Okay, so let's us move to the most exciting part about the demo session. So let's start from the beginning. So over here, what we are showing here is we are showing that we have two nodes for this demo. It's called RDMA node 1 and the RDMA node 2. And for both two nodes, we have trying to show RDMA resources at each of nodes. And then what we are going to show is the changes we made to the value YAML files to say how we enable the disaggregated PD. So for here, we are trying to show the YAML files from the tutorial directory on the production stack. So for here, for the prefilling pods, we have it running on RDMA node 1, and we request one RDMA resources. And for the LM cache configurations, and we have the NIXL CNI network, and that is the annotations that we mentioned on the last slide, on the previous slides, to showing that we have to let the pod to pick up the secondary network. And also we are having the UCX environment variable set up here to using the GDR. And also we are showing what we are showing here is for the prefill, the decode pod. That's where it's gonna run on the RDMA node 2, and also requesting one RDM resources. And similarly, it shows the environment variables and secondary network that we need to set up for using the GDR through the NIXL. And over here, what we are going to show is how the real deployments files looks like. So in this deployments files that we can see over here that we have the annotations for the prefill pods. That's where we pick up the secondary network. And so for here, we have the security context. And this security context is we have the privilege on the pod, so we can have direct access on the prefill pod. And for on the prefill pods, is actually we are going to see the same things. So for here, we still have the annotations for the second pickup to pick up a secondary network. But here we don't have the security context. And over here, we are missing the UCX the correct UCX environment variables for using the GDR. So we are going to install this Helm chart to see what's the performance looks like by using the same scripts. So similar thing here, we have one decode pod and one prefill pod. And we are also going to forward the pod here to run the benchmark scripts. So now we are moving to the VLLMs directory and to start running this benchmark script. The input command is exactly the same like what we showed previously. And over here, we are showing the screen, the recordings for how it runs. Although it's looks a little, it's a little bit, looks like a bit slower than the previous round, but it's actually much slower because we're trying to manage the time and speed up the recording over here a bit. But we are going to show what's the real performance looks like in this type of round to see how the time to first tokens looks different from the correct GDR setup for using the NIXL for cross node KVK transfer on the disaggregated PD. So over here, you can see that for the time to first token actually is super large. It's 81 seconds compared to our previous recording, the time to first token is just like 1.3 seconds. That's the huge differences between the two setups. So for here in this recording, we're just trying to tell that by correctly using the GDR, for this course node PD disaggregation, we can see huge performance benefits. And also for the demo, we are showing a few very important change that need to make the GDR being leveraged for this disaggregated PD. So let's come back to the slides. I'm trying to resharing the slides again. So that's all for the main context. That's the main of context of my presentation. So come to the conclusion. Like what we described in the first beginning of this presentation, the prefill and the decode this two phase. One is compute bound, one is memory bandwidth bounded. So these two phases, they stress the hardware in a different ways. And so that's help us to think about that. Probably we should try to scale this two-phase individually. So the disaggregation with the LM cache helps us to better align the resources and gives us the opportunity to scale two phases at course the nodes or course the GPUs. And when we try to have the disaggregation across the nodes, the GPU direct RDMA is essential for the course node KV cache transfers to help us deliver the good performance. So that's all for my presentation today. So thank you for listening, and I'm happy to take any questions.
Thanks Yue for the great talk.
Thank you so much. I'm stop sharing.
Okay. Any questions from the audience? Okay.
Thank you.
Yeah, with a great presentation. Okay, so our next speaker will be Ruoyu Qin from Tsinghua University. So Ruoyu is a PhD student in the Department of Computer Science and Technology at Tsinghua University, working in the Masses Lab under the supervision of Professor Minxin Zhang. His research focused on efficient machine learning systems with an emphasis on large-scale distributed LM deployments. Currently, he is an AI infrastructure research intern at Moonshot AI, a startup specializing in LM technologies. At Moonshot, he led the development of Mooncake, a KV cache-centric disaggregated inference system. His paper on Mooncake received the Eric Riedel Best Paper Award at Fast 25. Yeah, with that, Ruoyu, feel free to start sharing your slides and start your talk.
Sure. Thanks, Yuhan, for your invitation and the introduction. I'm sharing my okay. Can you see the slides?
Yeah, I can.
Okay. I'm beginning.
Okay, thank you.
Hi everyone. Today I'm bringing you a walkthrough of the Mooncake's open source components and also show how Mooncake integrates with Cache. I'm Ruoyu Qin. I'm one of the core members of the Mooncake team. Here is the outline of the for today's talk. First, I will start with a quick introduction to Mooncake. Mooncake is an internal serving platform for Kimi, which is a leading AM service provided by Moonshot AI. Mooncake was co-developed by Moonshot AI and the Kiwi Cache AI team at Tsinghua. The key idea behind it is trading more storage for less computation. By building a distributed global Kiwi Cache pool, it has greatly reduced Kimi's serving cost. The Mooncake paper was recognized with the Best Paper Award at the FAST conference this year. Our team is working hard to open source Mooncake. Right now, two of its core components, the transfer engine and the Mooncake store, are already open sourced and have been integrated into multiple LM inference systems, such as VM and SGLang. This slide shows Mooncake's architecture, which is a PD disaggregation architecture centered around a global Kiwi cache pool. The circled parts are Mooncake's core components, the Mooncake store and the transfer engine. On the right of the slide, you can see the overview of the open source components. The Mooncake transfer engine provides a fast, scalable, and fault-tolerant Kiwi cache storage system. On top of this high-performance engine, we built Mooncake Store, a distributed Kiwi Cache storage engine designed specifically for LM inference. As shown, Mooncake supports multiple storage and transport, and is already integrated into many frameworks like Mcache, VM, SGM, and Nixon. So the talk today will have two code walkthroughs. In the first part, I will show you the basics of how to use Mooncake's components. And in the second part, I will demonstrate how to use Mooncake as a backend of Mcache integrated with VIM. The first Mooncake component I'd like to introduce is the transfer engine. It is a high-performance Kiwi Cache transfer library, and its biggest strength is that it can fully leverage multiple RDMA network cards by aggregating their bandwidth. This gives it high performance for Kiwi Cache transfer. Compared with common collective communication libraries like NICO, NCCL, our transfer engine works differently. It uses one-sided read and write. That means communication doesn't require the other side to set up synchronized process groups. This makes it much better suited for online inference scenarios, where we often need elastic scaling and fault tolerance. Besides, the transfer engine provides multi-network card fault tolerance, load balancing, and support for multiple transports. If you are interested in the details, welcome to check out the online documentation. The second open source Mooncake component is the Mooncake Store. As shown here, a global cache system distributed. It's a global cache system distributed across multiple nodes. The diagram shows how Mooncake Store integrates with inference systems. You can see that there are two key components: the master service and the client integrate with VIM. The master service orchestrates the logical storage space pool across the entire cluster, managing node join and leaving events. It is also responsible for object space allocation and metadata maintenance. The other component is client. It can serve two distinct roles. First, it as a client. It is invoked by upper layer applications to issue put, get, and other requests. Second, as a store server, it hosts a segment of continuous memory that contributes to a distributed Kiwi Cache pool, making its memory available to other clients. Data transfer is actually from one client to another, bypassing the master service. Next, I will show you how to use these two components. We will follow the quick start section from the online Mooncake documentation. And we will get to the quick start documentation. The first is installation. Installation is very simple. We provide a PyPy view, so just use a single command to install it. Okay, this is my environment, just CLI. To save time, we have already installed most dependencies in my past environment, such as PyTorch, Mcache, and VM. So here, we will just demonstrate installing the Mooncake transfer engine. All right, it's very easy. Let's move on. According to the quick start, I will launch the simple transfer engine server and a client to show its simple function. This is my workspace. Copy it here and here. Okay, let me introduce these parameters. First, when we initialize the engine, the server engine or the client engine, we need to set parameters like host name, metadata server. We use the P2P handshake. You can also use etcd for better availability. And the third is the protocol. The example uses TCP, and here we use RDMA. The fourth is device name. For the transfer, we use write, transfer sync write. The parameter we need are other side's session ID, address, and the length. Here, we use ZMQ to communicate to pass this metadata. Okay, let me try to run this. On my machine, RDMA registration requires sudo, so I will run these scripts with sudo. So we need to get the Python parse. As you can see, the auto topology discovery has found all the 4 RDMA devices. Okay, the simple example is running very fast, and the 10 transfers is quickly finished. Now let's test its performance. We use the internode scripts to test its performance. I have 2 machines prepared, each equipped with 4 RDMA networks with a total bandwidth of 100 GB per second. Using the 2 scripts, we can run the performance test. Let me have a show. This is node 1. Before we run this, we need to get the host IPs of both machines. We use them, and this is node B. Okay. First, we will start the server. It is allocating a buffer of 20 GB and registering on it. Second, we start the client to test the performance. Transfer engine client internode. We need its host IP and the server IP. Oh, sorry. Its IP is okay. After 3 warm-up transfers and 10 benchmark transfers, it shows that the benchmark results showed that the average bandwidth is 78 GB. This result confirms that the engine nearly fully leverages the aggregated bandwidth of multiple network cards. Finally, let me show you Mooncake store. It is also quite straightforward. First, we will start the Mooncake master and the Mooncake HTTP metadata server, which are included in the Python transfer engine package. Okay. Okay, I will start Mooncake master. Mooncake master and Mooncake HTTP master service. And there is a very simple hello world example. It demonstrates the put and get API of Mooncake Store. Later, when I show the integration with IAM cache, we will see how this extends to multi-node distributed storage. And here is a very simple example. He put hello key and its value, and we get the key and print the value. Okay. After initializing the Mooncake store, it finished the put and get and print the hello Mooncake store. Let's move to the third part. In this section, I will demonstrate how we can integrate the Mooncake components with IAM cache and then apply them in VIM serving. Up to now, Mooncake can integrate into the VIM v1 engine in two ways. The first way is use Mooncake Store as the backend for IAM cache. This enables features like KV cache reuse and PD disaggregation. The second way is to use the transfer engine as the backend for Nixle, which can also support the PD disaggregation. This slide here is from the Mcache blog, just this. The title is Mcache and Mooncake Unite to Pioneer Cache-centric M serving system. The key message is simple. Mcache integrates Mooncake for enhanced performance, and Mooncake integrates Mcache for enhanced functionality. We have collaborated in many aspects to enhance to build a cache-centric IAM serving system. Welcome to visit the blog for more details. Now, let's walk through how to actually use Mooncake as a backend in IAM cache. I will show two features in particular. The first is KV cache reuse, and the second is PD disaggregation. For installation, we need VIM, IAM cache, and the Mooncake transfer engine. I already have this package installed in my Python environment, so we can just move to the demo. First is KV cache reuse. Let's following the IAM cache document step by step. First, it's just like the Mooncake store. We need to start the metadata server and the Mooncake master service. Okay, kill it. And then we need to create the Mooncake config file. We have built this. We have created. Note that with the current version of the Mooncake transfer engine, we need a small modification. For example, we remove the local device and we add a extra config that is sieve chunk meta and set it to false. After that, we need to start VM with Mooncake. Use this command. The model is Llama 3.18b. Okay. And if you use the Mooncake config, each VM instance will integrate with Mooncake stores client, and the client will connect to the Mooncake master service and contribute its segment memory to the distributed memory pool. But this is a single instance, so we just show the Kiwi cache reuse, not the distributed Kiwi cache pool. After set up the VM, we will run a simple client script to test the VM service to have a look at its function. Okay, let's send a simple request. Great. We can also run the benchmark script. Here, I use a random benchmark with a common prefix length of 7500. That means we can have a lot of prefix cache. Here is the command. We use 100 requests, and each request has 700 length. We can see that the requests are processing very fast and the throughput is very high because almost the input is prefix length and can reuse the Kiwi cache. These results clearly demonstrate the Kiwi cache reuse capability provided by Mooncake Store and Mcache. I killed the next, I will show how we can enable PD disaggregated serving with Mcache integrated with Mooncake. Let's follow the Mooncake documentation step by step. It is located here. First, we need to prepare 2 GPU-equipped machines and install the environment. The environment you need are VM, Mooncake, and Mcache. Second, on machine A, we need to start Mooncake master and the Mooncake HTTP metadata server. Here we start Mooncake master. Note that different from the documentation, I add a flag that is eviction evasion high watermark ratio and set it to 0.7. This flag is sorry. This flag controls the watermark at which Mooncake Master begins the cache evasion. By default, it is 1, but here I lower it to 0.7. Then we will launch the decode and prefill instance. To do this, we need to modify the disaggregated VM launcher file from the VM project, which is used to set up Mcache's disaggregated serving. In this script, here and here, we need to fill up the IP from both machines and run them with this script. This is decoder IP. And here we set a global queue cache size of as 30 GB, and we set 2 instances, so the total global queue cache size is 60 GB. Okay, finish these configurations. We will begin to start the decoder and the prefill instance. Models, wish it successful. And finally, we also need to start a disaggregated proxy server, which is used for routing. Okay, let me. Oh, sorry. Okay. The decoder and the prefiller instances are all set up. At this point, our PD disaggregated service is running. Let's test it with a simple client. It sends, sorry. Mm, there is a typo. Okay. Great, it works well. Now let's benchmark it again with the theme prefix sharing dataset. You can see that it runs also very fast. This confirms that with Mooncake and Mcache integrated, VM supports both KV cache reuse and PD disaggregation features at the same time. At the final step, let's test Mooncake Store's cache eviction mechanism. Remember that when I started the Mooncake master, I set the eviction watermark ratio to 0.7. Since our global cache size is 60 GB, this means the master will start evicting once usage exceeds 42 GB. Each eviction frees up about 10% of the cache following an LRU policy. We will run a stress test benchmark without a common prefix. And we can monitor the logs and see the cache usage and see how the cache usage is changing. The cache usage is quickly increased. Okay, at this time, we can see from the log that the cache eviction has already been executed. The size is also increasing. Let's wait until the benchmark finish. Okay, we can see that the master consistently keeps the cache usage under 70%. This prevents new cache pools from failing and ensures stable serving. And here is the PD disaggregation serving demo. We return to the summary. Okay, that wraps up my two demos today. First is the open source components transfer engine, and another is Mooncake Store, and the last is the integration of Mooncake with Mcache. Because of time, I couldn't cover all the features and optimization of Mooncake. If you are interested, I encourage you to check out the repository and the documentation directly. Finally, welcome to build your own projects with Mooncake and Mcache. And if you have any other questions or ideas about Mooncake, please feel free to reach out. I'd love to discuss them with you. That's all. Thank you. Thank you, Yuhan. Thanks, everyone.
Thank you so much, Roy, for the nice, really great demo and introduction to Mooncake. Thank you. Any questions from the audience?
Yeah, thank you for the presentation.
Thank you.
For the last example you walked through, is it the PD disaggregation or the cache reuse example?
I share this. You see the code or the slides? This?
Yeah, is there a link to the code you gave you ran?
Code. Okay. So what's your question?
Is there a link to the documentation that you followed?
Yes. All the code I run is follow the documentation either from Mcache and it's Mooncake and most of and another and the other parts are from the Mooncake documentation. Please visit our repository Mooncake and visit the online documentation. You can see all the getting started tutorials such as integrated with VRM, SGLang, and mdeploy and mcache. There are many tutorials.
Got it. Thank you. Yeah, seeing the cache reuse going up, it was really nice. Appreciate the talk.
Thanks very much.
Okay, thanks for the question. Any other questions? Okay, if not, yeah, let's thank Roy again.
Thanks, Yuhan. Thank you, everyone.
Thank you.
Thank you.
Okay, so our next speaker is Yue. Yue is going to talk about KV cache compression in LM cache. And just a brief introduction of Yue. Yue is a graduate student from Carnegie Mellon University working with Professor Beidi Chen. His research interests lie in the intersection of LM efficiency and system for LM. He received his bachelor's degree from Tsinghua University in 2023. Okay, Yue, with that, you may start sharing your slides and start the talks.
Okay, can you see my screens and my slides?
Yeah.
Okay, so my name is Yu and I'm now a master student in Carnegie Mellon University, and I'm also working with Mcache team about techniques and other integration things. Yeah. So today I will share some information about how to implement a simple KV cache compression algorithm in Mcache. Okay, so in this slide, we hope to introduce an intuition for introducing compression technique in Mcache. So for the long context inference scenarios such as RAG, we notice that prefilling cost is expensive compared to other parts such as decoding and especially for very long context, for example, 20Ks. So if you have stored the KV cache in a storage backend, and if we hope to reuse it, it will be a great opportunity to reuse the KV cache and significantly reduce the prefilling time and the corresponding time to the first token, DTFT. So here is a problem that due to the huge size of the KV cache for the long context, it would also introduce great transfer overhead and so it will heavily influence the end-to-end performance. In this case, we hope to introduce compression technique in this part. If we apply the compression technique in the storage backend side, we can heavily reduce the amount of the KV cache size, and then the communication overhead will be heavily reduced. In this case, the prefilling time will be decreased, and we will cost less time about the transfer. So in this end, we can save a lot of time and maintain at the condition of maintaining the performance, the end-to-end latency and the efficiency performance will be have a good gain. So this is why we hope to introduce KV cache compression technique, especially in the transfer side and the backend side. So we hope to introduce how to implement a corresponding technique in Mcache. In this tutorial, we will introduce the application in Mcache. So in Mcache, in Mcache scenario, there is one storage backend, which will show in the blue side, and it will store all the KV cache which has been pre-computed as trunk base. For the VM inference engine equipped with Mcache, when a long context prefilling and decoding is ended, the KV cache will be compressed and then sent to the remote backend storage. And one different inference engine means the similar or the same, exactly the same prevailing requirements. It will send a request to the storage backend and retrieve the KV cache, then loading the KV cache to its local GPU and do the further prefilling and coding sides. So basically, in Mcache engine, we implement abstract class called seared. So the seared will has two basic function which calls serializer and deserializer. For the serializer, we can the input is the full KV cache, and we hope to compress it and compress it to the bit stream object and then store it and then send it to the remote backend. So basically, in the remote backend, we will save the KV cache and the pure bit stream. And then for the deserializer, it will receive this bit stream from the remote backend and then decompress them to the using KV cache and then load them to the GPU for further calculation. So this is the high level overview of the how to implement the compression technique in the Mcache. So in this tutorial, we hope to introduce caching, which is an example to implement the similar or corresponding technique in Mcache. Caching is a fast context loading module for systems. It compresses torch tensor into bit streams and transfer the object between the engine and the backend. For caching, it has some features and contributions. For example, the first one is it will compress similar values with deltas, and the second one it applies layer-wise quantization, and for the third one, it applies smart arithmetic coding. We will introduce these three features as follows. So the first one is about compressing similar values with deltas. Basically, caching applies arithmetic coding to serialize the tensor into bit streams. Due to the time limit, we do not introduce too much about how to how the AC arithmetic coding works, but we hope to introduce some features about it. For the arithmetic coding, steeper CDF near zero implies low entropy, and so symbols need to so symbols need fewer bits on the average. This for this algorithm, we need to calculate the CDF as first, and then apply corresponding pipeline to compress all the KV cache into bit streams. So based on this feature in caching, we exploit exactly how we can use this feature of this algorithm to compress last bits with the KV cache. We encode the deltas of per layer channel using their CDF, which yields shorter byte streams than encoding the raw values. Notice that in this figure, how the red CDF rises much faster near zero, which means that many more small values and a tighter distribution. With delta CDF, caching introduce fewer bits cost in encoder side. And the second feature of caching is about layer-wise quantization. So in observation, we found that different layer has different tolerance for the quantization level. And for the lower computation layer, it has it can be more influenced by the by the same quantization config, and for the higher level, it has a robust tolerance. So based on this observation, we will apply the different conference config for different computation layers, and such layer-wise quant config will maintain the performance of the downstream performance. So for the third part, we hope to introduce some features about smart arithmetic coding of the caching. So basically, it is mainly around how to group tokens or how to group features into one slot and then apply the AC to compress it. It is mainly around the grouping algorithm. Caching applies better compression grouping for KV cache since we define a group as a single layer channel pair. For the K tensors, it will have the shape of layers, tokens, channels, these three dimensions. And fixing a layer and a channel will give us a 1D sequence across tokens. This means that we group the token level instead of layer level and channel level, and this sequence becomes one byte stream for the arithmetic coders. We do this for every channel and every layer, and we use the we implement a GPU kernel to realize such functions in parallel. This design is because group KV cache by layer and channels will give the most skew distribution for each group compared to other grouping methods. For example, group KV with by layer and token size. Yeah. So these three features is the main contribution of caching, and we hope to introduce these features for better introduction of future code reviews. Yeah, so basically, this is the main part of the slide side, and we hope to introduce more about the exact code about how the caching is implemented in Mcache, and and after the walkthrough, we hope to show a demo about how the caching works and the corresponding benchmark results. Yeah. Okay, so basically we hope to have a walkthrough of the code about how to implement the backend, remote backend, and how to implement the serialize function in Mcache. The main implementation is focused in the Mcache v1 storage backend dir. And in this side, we hope to introduce two things. The first one is about the connector. The connector means how we connect to the remote backend, and we can assume a backend, a connector as the connector to the DB side, and we just implement some simple DB functions, for example, put, get, batch group, batch get, batch put, and lookups functions. In this side, we will mainly use naive Mcache connectors. In this server connector, we just establish a remote backend, and we implement some simple functions such as exists, puts, gets. And for this, it is very similar to the database operation, which includes we need to input a key value and get corresponding value size. Yeah, so this is about how we construct the remote backend side. And for the compression technique application, it is mainly around the engine side instead of the backend side. In the engine side, we will connect these connector with the cert. So basically, we hope to introduce two basic functions for this class, serializer and deserializer, which will serialize the main memory object into the serialized compressed bit streams object, and deserialize will do the function vice versa. And here we hope to focus on these two functions. The first one is caching decoder, and the second one is caching decoder. For the caching encoder, we will introduce the config, caching config, read from the model. So for different model, we have different caching config for better downstream performance tolerance. And then we hope to introduce the deep look into the serialize function. So for this part, the serialize will do very simple things. You need to introduce a memory object into it, and then you need to do some shape operation to make it shape match. And then for the last thing, we need to introduce the encode function here. And the encode function will decompress and will compress and serialize the memory object into the bit streams object. So for the encode function, we give some basic notes of how it performs. The first one, first of all, it will quantize the key and value tensors into the corresponding range. Since we will introduce the maximum numbers, which we call the bins, in the caching config, and then all the key and tensor will be firstly quantized into this range, and then we apply the AC function to serialize it into the bit streams. First of all, we calculate the CDF with the quantized key and value tensors, and for this part, it will mainly implemented by a Mcache GPU kernel, and then once the CDF is calculated, we hope to truncate with corresponding hyperparameters, and then for each chunk, encode the token level tensors into byte streams with arithmetic coder. For this function, it is also implemented by a Mcache kernel, GPU kernel called encode fast new. So this is how the caching encoder does. And for the decoder side, it will mainly introduce the similar things, which implements the function vice versa. The input is a bitstream object, and the output should be a memory object. For this function, we hope to introduce this function from bytes. So basically, the bytes should be the bitstream which is directly get from the remote backend, and then and then we will perform a decode function GPU function to deserialize it and decompress it. So for this function, it is mainly designing these parts. Let me see. Oh, wait a minute. So basically, the high-level introduction endpoints of this series should be implemented in V1 dictionary, and the corresponding implementation and kernel size should be implementing the storage backend of Mcache dictionary. So we need to go back to this decoder size. In this decoder size, we hope to introduce this decode function GPU function, and then I think it will lead to the tensor memory object one. And for this side, it will do the reverse operations. The first one, it will turn the bit streams to the decompressed one, and then it will do the dequantization based on the caching key and caching config to the original key and value one. And the specific implementation should be down in the decoder. Let me see. Think it should be down. Yep. So it will be done by in this side. So basically, for this function, it will reshape the bitstream memory object, and then for each chunk, it will use a decode chunk function. And for this decode function, it mainly does the same GPU kernel, it will introduce a new GPU kernel, which is called decode fast prism, and then the bitstream will be converted to the tensor object, and then return to the decode function. So basically, you can see that most of the function is mainly done by the GPU kernels instead of Mcache side, since basically the Mcache side will construct all the function structures and introduce the main pipeline about how to firstly quant it and then serialize it into bit streams. And for the decoder, it will be the reverse operation. Firstly, deserialize the bit streams into the memory object and then dequant them into the one which can be fully used in the GPU computation. So we will have a deeper look into the kernel itself. So all the kernel is introduced in the C source sections, and for this side, we will mainly look into the decoder kernel and encoder kernel. So for the encoder kernel, if you remember, we mainly use the encode data CUDA new kernel, and in this side, the main step of it is to firstly introduce the CDF and the corresponding inputs, keep cache, and then perform the AC function. And for the decode kernel, we hope to have a deeper look. Yes. So for this decode CUDA new kernel, it will also introduce the corresponding CDF functions, and then CDF config, and then the corresponding bit streams inputs. So first of all, it will transfer it with the CDF with a packed ancestor 32 function into a readable version, and then it will call the corresponding kernels about how to perform it in parallel. The hyperparameter should be the block size, and in this side we can have a deeper look into how the corresponding kernel works. So this kernel should perform the detailed decompression side. For this part, the first step is we hope to load the prefix sums for this tile into the shared corresponding positions. And for tile entry I, we need start equals to prefix I plus 1 and equals to prefix I. And then for the second step, we need to load the bitstream into this tile into the shared block size values and load them into the corresponding positions. And the third step, we need to load the CDF for this tile into the shared block size. This is also has a detailed description about how this position works. And for the fourth side, we hope to apply the detailed arithmetic decoder states, which will be similar as other kernels. And for the last step, we hope to detoke and token symbols. And after all these sides, the kernel should already write the corresponding tile, which should corresponding to one layer 1 channel object of the whole KV cache. And this is how the encode and decode kernel works. Okay, so basically this is how we have a detailed code walkthrough about the caching compression technique in the Mcache side. So similarly, if you hope to introduce something, another quantization technique in Mcache side, you can do a very similar things with how the caching is integrated. So basically, for this side, you need to introduce subclass which is derived from this abstract class cert, and then implement your own serialize and deserialize function, which will compress the KV cache and decompress KV cache. Mcache side will help you automatically set up other things. For example, how to load the KV cache from the GPU to the CPU side, and then how to load the KV cache from the CPU to GPU side. All the works is around after we have already loaded the GPU memories and corresponding KV cache, and how we do the quantization and dequantization operations in the next step. And if you hope to introduce something other quantization methods, for example, KV quantization or Q-serve quantization, you can just implement your own version and apply it into the remote backend. So this is about how to implement compression technique in high level about into the Mcache framework. So in the last part, we hope to introduce something more about the example demo about of how to run the caching Mcache site. I will share the screen about the demo of it. Yeah. So basically, this is about this is an example how to establish remote backend, and then how to establish different inference engines based on this backend, and then reuse the KV cache. So in the first window, we hope to firstly establish a remote backend, which is exactly a KV cache, Mcache connector. And then in the second window, we hope to introduce the first server, which will run Llama 8 billion model on one H100 GPU. And for the third window, we hope to establish the second inference engine, which will also run Llama 8 billion models on another GPUs. And then for the fourth side, we hope to introduce a benchmark script to run to see how the performance will be look like and how the performance will be how the efficiency performance such as TTFT and TPOT will be reduced by a caching operation. Yeah, so in this side, we have already established the remote backend setup, and in this period, the two inference engine is not working and starting. After the inference engine is set up, it will has a connection with a remote backend, and the remote backend side will show the corresponding information. For example, it has already connected a client from the corresponding portal, which means that it should be the inference engine, which will hope to connect to this backend server. Okay, I think in this side, yeah, in this side, you can see that in the remote backend, it has already connected by two different inference engines, and then which means that the engine is already started up, and in this part, we hope to start our benchmark script. So for this benchmark, it should be a long benchmark scripts which will introduce the efficiency performance, which will show the efficiency performance of how the inference engine works on very long context prevailing scenario. And in this scenario, we hope to use the narrative QA dataset of Longbench. It should be a very quick benchmark, which will last, for example, something like 5 minutes. So the full size of the data set of the benchmark should be 115 points. And the throughput should be equal, the QPS should be equal to 1. So this should be a very low QPS. And we hope during this benchmark, we hope to see how the TTFT and TPOT works. We can introduce the first benchmark outputs, which will send to the first server we set up. In this site, there is no KV cache pre-computed, and so all the KV cache is computed in the first server and then sent to the backend. In this site, you can see that the main TTFT should be something like 8 to 9,000 milliseconds. This is a very high number, and also the time for output tokens and internal token latency is also very high. So we will do the same benchmark into another server, which has the portal of 8071. For the first benchmark, the portal should be 8070, since this is two different portals for these two servers. And then after the pre-computed KV cache, if we will send the same exactly the same request to another server, it will firstly retrieve the corresponding KV cache to the remote backend. And in this side, we have already stored the pre-computed KV cache in the storage backend. So it will send the corresponding bitstream object to the inference engine, the second server. And then we hope to see that the reuse of the caching, the reuse of the KV cache can introduce a better efficiency performance. So we can still speed up all the process and then directly jump to the final outcome. Yeah. So basically, the outcome is the second benchmark theory shows the how the caching can improve the efficiency performance. So basically, we can compare with different metrics. For example, the first one is about the time to first token. You can see that the time to first token has already dropped from 8 to 9,000 milliseconds to around 1,000 milliseconds. This means that the prefilling time is heavily decreased. Actually, we for this side, we do not need to compute all the prefilling KV cache. Instead, we just need to load all the KV cache from the remote backend into this inference GPU engine, and then load it to the corresponding GPU buffers. Yeah, so this is so I think this time it mainly shows how the transfer time and how the loading time works. And for other efficiency metrics, for example, time per output token and internal token latency, it will also show relative decreasement, since the heavy is the computation heavy the computation overload is decreased by the pre-computed KV cache, and all the system end-to-end inference efficiency can be benefits from the corresponding technique. Okay, so basically these are the main parts of how the how the compression technique is established in the Mcache framework. And I think for the next 10 minutes, it should be the QA time. Yeah. Thanks. And I will introduce back to the slides.
Hey, thanks, Yue, for giving the great talk. Okay, any questions from the audience? Okay, if not, now it's afternoon break time, and the next session will start at 4:15, which is about half an hour. Okay, thanks everyone, and see you in about like an hour. Okay. Okay, hi everyone. Welcome back. So the next speaker will be Shaoting Feng. Shaoting is a pre-doctoral master student at University of Chicago, advised by Junchen Jiang. His research focuses on systems for large language models and computer networking. He is also one of the core contributors and maintainers of our open source projects on Cache and VLM production stack. Hey, with that, Shaoting, you may share a screen and start the presentation.
Hi, I'm shouting. Can you see my screen?
Yeah, so but it's in the presenter mode.
I think this is correct.
Yeah, right now it's good.
Okay, thank you. This session it's about running the multimodality models with LM cache. The overview is that VLM is building on its multimodal compatibility and currently supports a lot of multimodal language models. The input can be text or the audio or the video or some images. LM cache is built on top of VLM and can therefore be used to speed up inference time for all multimodal models supported by VLM. And in this session, I'm going to walk you through some examples to show the speed up with cache on these multimodal models. And then I'm going to share the principle of cache about how it handles the multimodal input. Some requirements of running cache and VLM is having a sufficient GPU, and in the examples in this session, I used a one H100 GPU and install VLM and cache. One special note is that if we want to use the audio models with VLM, we need to add a bracket and put audio inside when we install the VLM. The first example is about the audio inference. I used the audio from our latest LM Cache team community meeting, and it is a 19-minute audio. And I choose a model, Ultravox version 0.5 Llama 3.18b, and using the LM Cache V1 connector. In the VLM requirements, the input audio can be based 64 data, and we need to put the explicit format in the input, or we can put the audio URL or the local data URL of this audio. This is a screenshot of the example of audio inference. The left side is VLM and LM cache engine log. And on the right side, we can see in the first request, the TTFT is 6.139 seconds. And for the second round, the TTFT is 4.540 seconds. And the speed up comes from the KV cache reuse of the same audio. And we can see from both log, the output is correct. In the first output, it summarizes the meeting information. And in the second round, it extracts some important info of the meeting. And this is the engine log of cache. We can see for the first round out of the 7,200 tokens, cache didn't hit any tokens. And in the second round, cache hit all the tokens. Therefore, it brings a speed up in the TTFT. The next example is running the image inference with QVAN model. And the image I choose is a Yosemite National Park map, and it is a 1.8 megabyte image. We start VLM and cache with the same command and using the Q12 BL2B instruct model. And the input image can be both an image URL or a local URL or a base64 encoded image string. When we input the image for the first round, the TTFT is 4.234 seconds. And in the second round, the TTFT is 0.7771 seconds. I didn't show the streaming output, so you may see some delay because the decoding delay, but the TTFT is measured correctly. Cache reduces TTFT by KV cache reuse. We can see out of the 12,000 tokens, cache hit all the tokens in the second round and therefore brings a speed up. The next example is about running multiple image inference with Phi 3.5 vision instruct model. In some of the image models, they support inputting multiple images in a single query. And I inputted two images. The first one is a national park map from the last time, and the second is an image of delta of the river in Tigray, and it is also a large image. We can see in the input, I limited the multimodal per prompt as two images, so I can input it for both of these images. And from the log, we can see the first round. TTFT is 4.427 seconds. And in the second round, the TTFT is 2.833 seconds, and that is 1.56 times TTFT improvement. And we can check the output of both rounds. Both rounds identify the first image is a detailed map, and the second round is a landscape with some sky reflection. And out of the 1,534 tokens, cache hit all the tokens in the second round and therefore reduces the TTFT. The last example is about video inference. This video is an advertisement. It's an advertisement of the Google Chrome HDMI, and it is widely used in the multimodal video input. I use the model Lava One Vision Q12 7B OVHF model and uses the cache V1 connector. And similarly, the input of the video can be either a URL or as a base64 encoded string. And for the first round, the TTFT is 2.465 seconds. And in the second round, the TTFT is 2.056 seconds. Cache hit more than 6,000 tokens in the second round and therefore reduces the TTFT. Now I'm going to introduce some principles behind cache. For the regular model, when we input the text, there is a tokenizer that tokenizes the text into some tokens. And then using a map, the tokens can be injected to embeddings and they serve as the input of the large language model. Similarly, for the multimodal models, the input can be image, audio, or video, and they will go through different encoder. Like the image has some image encoder using the pixel, and the audio will go through the audio encoder. And they will generate the embeddings of the multimodal input. But the multimodal input and the text but the multimodal embedding and the text embedding may of different dimension, but they need to be aligned to the large language model hidden sites. So the multimodal embedding will go through a projection or the adapter layer and become the aligned multimodal embeddings. Now, the text embedding and aligned multimodal embeddings are tensors of the same dimension, and they can be fused together to serve as the input of large language model. The fusion can be a simple concat or some cross attention according to different models. So on the high level, why do we want LM cache to support the multimodal input? We can see for the images can be very large if it is very clear, high resolution, the image can be multiple or even tens of megabytes. The video and audio are larger, so the KV cache may be very large for the multimodal models. But during the experiments, we have found that the encoder of the multimodal models are actually well designed, so the embeddings may not be very large in reality. But we can see from the image models, the KV cache is still very large, and the improvement is very high using the LM cache. So from the last slide, we can see the text input and the multimodal input. Large language models see them as same embedding. So we only need to figure out how to represent this input. On the high level, LM cache stores the KV cache as multiple memory objects. And for the text input, LM cache uses the token IDs to identify and match the KV cache memory object to the original input. But the multimodal input, they use dummy tokens and placeholders in the token ID field for the large language model to see. But fortunately, they have multimodal hashes to identify and match the multimodal input. So for different input, like for different images, they have different multimodal hashes, and we can use the hashes to identify and match the KV cache memory object. We can go through the LM cache behavior. So in the VLM, when a request comes in, the orange part represents the text and the blue part represents the multimodal input, let's say an image. And the VLM v1 uses the chunk prefill as default, and it is chunked into 4 chunks. And the blue part now becomes the dummy token IDs. And each chunk is then offloaded to LM cache sequentially. When we do the offloading, LM cache replaces the dummy token ID with the multimodal hashes. So for the red part inside the LM cache engine, the LM cache can differentiate between different images, and then it can avoid being cross-reuse KV cache like mistakenly. And each input can find its correct KV cache when the input is reused in the second round. And when we perform a lookup in the VLM, the LM cache connector will replace the dummy token IDs with the multimodal hashes, so it can inform the VLM how much KV cache is already stored in LM cache and do not need a prefill. And this is a principle of VLM and Elm cache about how they handling the multimodal input and how Elm cache speed up the inference time. Thank you. Is there any questions?
Okay, thanks, Charlene, for the great talk. Any questions from the audience? Okay, if not, let's thank Shouting again. And our next speaker will like the next session will be in 15 minutes. 15 minutes. Yeah. Let's take a short break now and see you guys in 15 minutes. Okay, since our last speaker is here, let's start the session early. Xiangfeng is the last speaker, and so Xiangfeng is a PhD student at Paul Allen School of Science and Engineering at the University of Washington, advised by Arvin and Ratu. His research interests are broadly in computer systems and networking, and his recent works have focused on microservices, service meshes, and application networking. Okay, with that, Xiangfeng, you may start sharing your screen and start your talk.
All right. Thanks for the introduction. Let me go ahead and share the screen here. Is my slide visible?
Yeah.
Okay, cool. Yeah. So today I'm going to talk to you about auto scaling with LM cache. And before I start, why we do auto scaling? So the main reason is that the ideal resource allocation of a given application depend a lot on the workloads. And one of the characteristic of large language model inference is that the workloads are very bursty and unpredictable. And the result of that is if we decide to put too few resources, it can lead to very bad user experience in terms of high latency, especially tail latency, and even outages. But if we provision too many resources, it can lead to wasteful, expensive results. We all know that GPUs are very expensive these days. And this quickly walk you through the workflow of auto-scaling. So typically workflow when you do auto-scaling in Kubernetes setting is that first you want to collect metrics. And in our case, it means that we expose certain signals to Prometheus, which is a metrics collection platform we use to collect metrics from the router and then expose them to the external API. And then once you have the signals collected, you will need to define certain scaling rules. And there are multiple autoscaler exist in Kubernetes, most popular ones being the HPA, which stands for horizontal pod scaler, and there's another autoscaler called KEDA, which is stands for Kubernetes event-driven autoscaler, which will be the main focus of this talk. And then so you need to configure the autoscaler with the custom metrics you want to use. And I will touch more on what metrics means in a sec. And then lastly, once you have those defined, the autoscaler can kind of autopilot. So it scales pod up and down based on the threshold that you define. So concretely and visually, what it means in element cache. So whenever users send a request, the router will route the request to the backend VLM engines. And here we have two engines with multiple replicas per engine, or multiple replicas per model. So when the user sends a request and get a response, the router and engines internally collect a number of metrics and then report it to the Prometheus platform. Then the Prometheus platform will process the metrics, and then the autoscaler that are defined by the user will collect the signals or collect the metrics from the Prometheus API, and then internally have some logic to do autoscaling, and then eventually decide a number, which is the number of replicas there should be per engine. And then it will send to the Kubernetes controller API such that it will auto scale based on this number for you. And let's talk a little bit about the most important piece, which is what signal you use to drive the auto scaling. So it can be mainly fall into three main categories. So first, it can be request driven. So you can autoscale based on the incoming request QPS query per second, or you can have an internal queue length, which the router internally maintain a queue length for the number of requests that are pending. Those can be a good metrics to use for autoscaling. It can also be resource driven. And here you can define auto-scaling rule based on the GPU utilization. For example, if the GPU utilization reach, let's say 80%, you auto-scale based on that. And GPU memory sometimes can also be a good metric to use. And lastly, you can be more latency driven, which is like more outside effect. You could use the tail latency such as P95 or P99. Oh, it's typo here, but P99 service time as a metric to scale your workload. Or you can even use a combination of all of those. For example, you could use both tail latency and GPU utilization as a signal to define scaling. Yeah, let's do a demo. Before I jump to demo, any questions so far? All right. So here I have a simple Kubernetes cluster set up with a router deployed and a single Llama model deployed. So there's only one single replica of them, and this goes back to the figure here. We have a router, and we only have one engine with one replicas. And then here I can show you if you send the request, you'll get a response in reasonably time. And then on the right, I have Prometheus dashboard, which shows you two things. The top panel shows you the incoming request rate, which is like how many requests coming in per second. And you can ignore the spike here, which is I used for testing earlier. And then the second panel, the lower panel shows you the pending request, which the router internally it maintains a queue that for the pending requests. So those will be the two signals we use for auto scaling for this demo. And then you can see if I refresh it, you see the spike it got populated to the Prometheus dashboard. By the way, so the dashboard I'm using is called Grafana. It's not Prometheus, but it's more like a external API, external service that script the metrics from Prometheus and then visualize the metrics for you. And now let's try to define auto scaling policy. Here, here is a simple one signal auto scaling for Kata. There are a couple of important pieces here. First is you see this min replica count and max replica count. This means that the min replica list will autoscaler will put to, and then this max means the maximum. And then there is pooling interval, which is how often should Kata check for these metrics when deciding autoscaling. So the longer the pooling interval, you can see the longer the duration will take for the autoscaling to take effect. And then there's also a cooldown period, which essentially means how long the autoscaler should wait before scaling down after a scaling up. This prevents you, if the metric oscillate quite often, it prevents the autoscaling from scaling up and down frequently. And lastly, the trigger session defines the triggers we want to use. In this case, we only have one trigger called number of requests waiting, which is what lower panel shows you. And then the threshold is 5, which means that if the queue length exceeds 5, Kata will trigger a scale up. Yeah, let's see it in action. So I'm gonna start a load generator, which send roughly 100 requests to the service, and oops. And then let's do send the request, and then let's go to the cluster panel. If I refresh it, like this configuration suggests, you have to wait at least or at most 15 seconds before you will see any auto scale up or scale down effect. So let's see. I hope this. Okay, here, yeah. You see there are 80 requests pending, which means we did get the load generator is working, and then oh, great. Sorry, I forgot to apply this. Yeah, let me see. So what we need to do is apply this configuration. So we'll run assets, and then values 20. Okay, yeah. And then once this is applied, you should see in a moment that this will be, I hope it's not too late. Okay, you can see here, you can see there's one additional replica being brought up by the autoscaler, and it will take a couple of minutes for it to spin up. So while it's doing this thing, I will show you how to use two resources for scaling up. And here, one of the advantages of Kata versus the native Kubernetes horizontal pod scaler is that Kata support scaling down to 0. So let's say when you in a period that is no request coming in, you can essentially save you money by reducing the number of replica to 0, and then you can scale up when there's a single request comes in. So here, this configuration, which I will not attempt to run because it takes a long time for a engine to spin up. Here you have the second trigger. The second trigger means that when there's a request in the last minute, you trigger a scale up. So this query will return 1 if there's any incoming request in the last minute, which essentially is the top panel shows you. So this allows you to scale up even there's no backend engine available. All right, any questions before I move back to the slide? Okay, so let's talk about some of the future work that we are doing here. So an important theme of large language model workloads is that it's very different from the traditional web applications, and they're different in multiple ways. First, the workload characteristic is very different, and they're heavier. The engines are low running, and then they're mostly GPU bound versus CPU bound for the most web applications. And second, you likely need to use different scaling metrics for both workloads. The traditional scaling metrics for web application are request rate, queue length, and latency, which might not be a good fit for the large language model serving workloads. The main reason is that in web applications, the requests are roughly uniform, which means that they roughly take equal number of resources. However, in large language model workloads, each request may have drastic resource consumptions. For example, if a request with long token, it naturally take more resources than a request with lower number of tokens. And also, it also implies latency could be quite different even for different requests with different token lengths, also context lengths. And then secondly, the scaling latency is different. Cold start of traditional web application can be very low because they have very low profile. The images can be just several megabytes. However, the cold start of large language model engines can take minutes of loading. You have to load everything to GPU memory and set up the context. And in our case, the llama model we use takes roughly 5 minutes to spin up, and which you can see, yeah, it roughly takes 4 minutes for this demo. So the scaling latency is very different. It has quite high impact on, let's say, if you provision too few resources, and then the cold start will give you bad user experience because the cold start of large language model engines. Yeah, that's it for the talk, and I'm happy to take questions.
Hey, thanks so much, Xiangbo, for the great talk.
Thank you.
Any questions from the audience? Okay, if not, let's thank Xiangbo again for the great talk. And yeah, okay,
Everyone.
thanks. Yeah, so this is our last session. And so let me do a quick recap of what we have covered today. Um, one moment. Okay. So yeah, thanks everyone for coming to the our full day tutorial at SIGCOMM today. So today we have talked about like a overview of distributed our inference systems and on cache, and we have talked about how to set up and do a simple one-click installation of on cache. And we have covered like ways to deploy on cache in an agent application. And you have seen like how to visualize the speed up brought by on cache with Grafana dashboard. And then we have talked about the integration of on cache into VLM and how to run disaggregated prefill with on cache. And we have also talked about like Mooncake integration with on cache and how to do a simple KV cache compression in on cache. Finally, we have covered like how to run and visualize the speed up when you run a multimodality model with on cache. And finally, we just covered like how to do auto scaling with on cache. Yeah, so that's a quick recap of what we have covered today. And just want to mention that here are some resources you can check out if you are interested in on cache and interested in trying it out. And also feel free to join our Slack channel. And you can also submit any issues. And if you want to contribute back to Cache, you can also submit a PR to Cache repo. And yeah, so if you have any questions, like you can shoot me an email. Okay. Yeah, any more final questions for our team? Okay, if not, like that's the end of the this full day tutorial. Yeah, thanks everyone for coming, and it's a great time talking to you guys. Okay, thank you. Bye.